Sure, of course. Yeah. It's the morning after the conference banquet. Yeah. Gotta let people sober up. That's okay. I can see the clock. It's fine. Yeah. It was a party last night.
So good morning, everyone. I hope we're not feeling too tired this morning. This morning we're moving on to staff measurement on intermediate and galactic scales. I will be the sweetie dispenser, and Mark assures me that he's got questions for us this week. So, Mark.
Yeah, there we go. That's really all the intro I need. So I have been charged with talking about the formation and properties of giant molecular clouds. All right, apparently I need to stand a little closer. So here's the outline. I'm going to sort of start with just a review of the basic observations, and then I'm going to talk about the GMC life cycle, focusing on birth, evolution, and star formation, and then death. Although I will not say a whole lot about death because Melanie covered a lot of that not Melanie. It was Melanie's slides in my defense. Yes, pseudo-Melanie. Melanie Prime. Covered a lot of that in her lecture. All I apparently need to stand on this side if I'm going to be within range of the, there we go. So let's start with the observations. This is a picture of me. I've gone observing once in my life. I was taken pulsar observing at Green Bank when I was, a first-year university student, and let's just say I'm a theorist now. I don't know if any of you have ever been to Green Bank, but if you had, you'd understand why. All right, so I think it's worth starting with just looking at some pictures of when we talk about giant molecular clouds, what do we mean? What do the data actually look like? All right, because I think it's worth, just keeping in mind that. So here I have two views. One, a typical sort of extragalactic observation, typical galactic observation. All right, so here is an image of, I can't remember exactly which galaxy this is, in the CO1 to 0 line. And you zoom in, and it looks something like that. And then you look at this and you say, clouds, and you somehow decide to break this up into lumps, and you say that's giant molecular clouds. Or, if you're within the galaxy, right, this is the good case. This is the case where you actually can see clearly what's going on. This is the bad case. This is the case where everything is confused, and you have to try and break stuff up using the velocity dimension. So this is just a piece of the galactic disk, and this is in longitude, but this y-axis isn't from Marc-Antoine Miville-Deschênes' work. And this is what the data look like. And again, you sort of look at this and you're like, clouds. That's a cloud maybe, or maybe that's a cloud. Is that a cloud? Right, so this is, I think, the first lesson we have to keep in mind whenever we talk about giant molecular clouds, is that a giant molecular cloud is not like a well-defined thing. It's not a star. Stars have edges. Molecular clouds do not. If you zoom in up close, they look something like this. Right, so the answer is you have to just make an arbitrary decision, and then every statistic you give is relative to that arbitrary decision, right? There are real chemical edges. That is, there is some point where, for example, the carbon goes from being carbon plus to CO, and the hydrogen goes from H to H2. And we'll talk about those transitions in a little bit, but it's unclear that they are of any dynamical significance, right? The fact that there's been this chemical change doesn't imply that, for example, corresponds to a transition between bound and unbound material. If you're using dust observations, you don't even know where those chemical boundaries are. You can draw contours, all right, but how do you choose which contour level is the right one to define the cloud? And the answer is there isn't one. There's no unique way to define giant molecular clouds. So an important thing to keep in mind is that whenever anyone gives you molecular clouds have masses of blah, or sizes of blah, or any other statement they're making about molecular clouds, you have to remember that statement is always and invariably relative to some particular way of defining what a cloud is, and if you chose a different way of defining what a cloud is, those things would change. All right, so that's just a critical thing to keep in mind. Now, this problem has led some groups to just give up entirely on the idea of defining clouds and just do things like pixel statistics. Basically just say, all right, we're not going to try and break this blobby image up into objects. We're going to pixelize the image and give you the statistics of, here's the luminosity distribution in pixels or something like that. And that is, in my opinion, often a better approach. Nonetheless, we're stuck with the tradition of molecular clouds, and so that's what I'm going to talk about. I have to walk back over here every time I want to change slides. All right, so with that caveat in mind, what are the basic properties of GMCs? Well, all right, so here's, for galactic GMCs, again from Marc-Antoine Miville-Deschênes' paper, just some basic histograms of properties. And what you see is, all right, surface densities are of order tens of solar masses per square parsec typically. All right. Masses, they don't focus on the low mass end because that's incomplete, focus on the high mass end, and the mass spectrum is something like 10 to the minus 2. Typical sizes are like, tens of parsecs. Typical densities are, tens. So those are some typical numbers, but again, just going to keep reminding you, this is relative to some particular way of defining what a molecular cloud is. All right, now, you can, from this density, immediately deduce a time scale, which is the free fall time is of order 10 megayears. And that's the natural time scale on which you expect GMCs to evolve. And that's going to come up again later. Oops, and there we go. Fuck it. Okay, so size, which I'm now. All right, so let's think about it, right? I mean, clouds aren't spheres, but they're not anything, so they might as well be spheres. That's not like worse than wonders. All right, so let's consider a spherical cloud of some mass and radius and some velocity dispersion. If cloud kinetic and gravitational potential energies are sort of scaling roughly with one another, how would you expect the velocity dispersion to vary as a function of radius and surface density? So this is where you take out your piece of paper and do a quick calculation. So someone tell me the answer. First person to answer gets chocolate.
There is chocolate in it.
Tutors can't answer. I mean, you can't answer, but you don't get any chocolate.
Yeah. Oh. Whoa. The velocity dispersion should be proportional to the mass, right? So.
Well, all right, so tell me your reasoning.
It's like for the bigger reason, the more mass is like more gravitational force. So.
Well, I mean, so I agree they're going to depend on one another, but is the relationship linear? I mean, I was suggesting, could you write it in terms of R and sigma?
Not sure.
Or if you wanted to, or in terms of M and R. I'll take in terms of M and R. How does it depend on mass and radius? All right, I'll give you a hint. If we're going to do it in terms of mass and radius, how does radius? I want to calculate the escape speed from the surface of the Earth where I'm standing right now. How would I do that? Bueller? Yeah, okay, that was one of those jokes that the tutors in the back got, and all the students were like, what the fuck are you talking about? Go look up Ferris Bueller's Day Off when you're done. But do math first. No one's going to get the chocolate? I'm going to eat the chocolate in front of all you suckers if you don't someone doesn't answer. If I were to increase the mass of the Earth by a factor of 10, how would the escape speed change? What was that?
There is r to the power of minus 1 over 2.
Okay, and that's how it varies with radius. And how about mass?
Oh, I've missed the mass term. Good. Completely forgot about equations there. Proportional to root of mass. Can't do math. Well, it scales mass to the power of 1 over 2.
There you go. Give her a chocolate. Yes. All right, the escape speed goes like square root of gm over r. All right, this is one of these formulas that you should just keep in your head. Velocity goes like square root of gm over r. Right, escape speed, you put a factor of 2 in front of it. Virial velocity, some other factor. Don't care about factors of order unity. Square root of gm over r. All right, you can also rewrite that in terms of surface density because the range of, and the reason we tend to do that is because the range of surface density is a lot smaller than the range in mass. So if you just work out what it is in terms of surface density, you get the following relationship. You get that sigma v goes like square root of r times surface density is what you expect if kinetic and potential energy scale with one another. And lo and behold, that's basically what you observe. Right now, people have great arguments about, does this mean molecular clouds are bound? They define this thing called the virial parameter. All right, and holy wars are fought over what this means. I don't really care. All right, what I want to take from this is simply that kinetic and potential energy are roughly scaling with one another. All right, that's what I want you to take from this. And that most of the mass, at least for big clouds, And this is where most of the mass is, right? Most of the mass lives in clouds, lives in these clouds. Again, for some definition of cloud. All right, so this relationship between the velocity dispersion and the size is called the line width size relation. All right, and it's one of, you may have heard of the term Larson's laws. It's one of Larson's laws. All right, the final thing I want to sort of say about GMCs and their bulk characteristics is I just want to talk about time scales. All right, so I mentioned before, the most basic time scale you can define for a GMC is the free fall time. All right, square root of 3 pi over 32g rho. And that is simply the time it would take a spherical blob of gas with 0 pressure to collapse to infinite density under gravity. That's the natural time scale on which any self-gravitating system evolves. All right, and you can work out what that is, and you get, numbers of order 10 megayears. All right, you can also give the crossing time, which is like the size divided by the velocity dispersion, but it turns out that that's basically the same as the free fall time, modulo factors of order unity, if kinetic and potential energy are comparable, which we just saw that they are. All right, so this is the natural time scale, and then there are other time scales we're interested in, and that we're going to talk about as we go through. One is the depletion time. How long would it take to convert all of the gas in a molecular cloud into stars? The other is the lifetime. How long does an individual GMC live? Which, again, is somewhat nebulous because we have to define live and GMC. Nonetheless, it's interesting. So we want to know what these timescales are relative to the free fall time, because that's going to be informative for us. All right, so that's what we've got with bulk characteristics. Now let's start talking about the GMC life cycle. All right, so here's our current understanding of the GMC life cycle. This is another one of these, like, all right, raise your hand if you recognize this reference. Oh God, we're fucking old. Okay, your second homework assignment is to go Google South Park. All right, and or underpants gnomes. You'll thank me. Yeah, yeah, Amy's laughing, Joey's laughing, all the students are like, what are you talking about? All right, it's ancient history. All right, we've got the pyramids, we've got, we've got like, guys with swords on horseback, and then we have the underpants gnomes. Just part of human history. I remember when, the first South Park, like, it was the original viral video. The first ever viral video was the basis of South Park. I am so old, I remember when there was no such thing as a viral video. That's how old I am. All right. What do we want to know about the GMC life cycle? All right, so basic questions we'd like to answer. How and why do GMCs form in the first place? Once they're formed, how long do they live? And what fraction of their lives do they spend not forming stars versus going away? How rapidly and efficiently does star formation take place when they exist? And then what eventually ends GMC's lives and limits the fraction of their mass that they're able to convert to stars? So let's start with the first of these questions, the sort of dynamics of how do you assemble a GMC? And the answer is, I mean, again, this is one of these things where like 10 years ago, there were great holy wars over like, did GMCs form by Touré instability or converging flows or supernova-driven shell collisions or cloud-cloud collisions? And the answer is a little from column A, a little from column B, a little from column C. All right, and if you actually do simulations where GMCs are forming, I'm showing one here from the Tigris group at Princeton, Kim et al., you see it's a little of everything. All right, and the fundamental reason is that in a galactic disk, the energy in sort of supernova shells is about comparable to the gravitational potential energy, is about comparable to the velocity dispersion, is about comparable to the turbulent energy. All of these things are the same order of magnitude, and so all of these things can assemble gas into lumps. All right, so this is how we think, GMCs come about. But assembling the gas is only part of the problem, right? What makes a GMC is the M part, the molecular part. So how do we get molecular gas? Now, I could talk about the CO, because that's the thing we observe, but my time is limited, so I'm going to focus instead just on the H2. So let's talk about how do we get molecular gas in galaxies. And to answer this, we need to delve into the horrible H2 molecule. All right, and what do I say horrible? Well, you think, okay, like this is the simplest possible molecule. There's 2 fucking atoms. The simplest possible molecule. That should be simple. Oh God, no. All right, like even the simplest possible molecule is horrible, horrible. So I am now going to take you on a tour through that horror, understand why H2 acts the way it does. So let's start with a basic mystery, right? The molecular form of hydrogen is a lower energy state. H2 molecules have a binding energy of 4.5 eV. So why do we find most of the ISM filled with not molecular hydrogen, right? That's the higher energy state. Why is most of the ISM in the higher energy state rather than the lower energy state? Why is it filled with atomic rather than molecular hydrogen? And to understand this, we have to understand the processes that form and destroy H2 so we can understand when they'll become dominant. And here's the key physical constraint. Here's where the horror begins. All right, so the most obvious thing you'd say is, well, all right, I want to form an H2 molecule, so let me take 2 hydrogen atoms and slam them together. And if they're going to become bound, well, maybe I can radiate a photon and that can get rid of the energy, and that's how I form H2. And that doesn't work. And it doesn't work for the following reason. Now I'm going to drag you back to like the quantum mechanics class you've repressed. So in your semi-classical perturbation theory, you say, all right, I want to know the rate at which some process occurs in perturbation theory, right? So I take the initial state and I take the final state and then I take the perturbing Hamiltonian between them and I make my bra and my ket and I calculate, do a bunch of horrible integrals and I get a matrix element and I calculate the transition rate. All right, you can do that for radiative processes, and to leading order, emission of a photon is described by the electric dipole operator, semi-classically. All right, so I take my initial state, my final state, I put the electric dipole operator in the middle, and I evaluate this integral. And here's the problem. D is the electric dipole operator, as the name implies. It's dipole, it's mirror antisymmetric. Both the initial state, say 2 free hydrogen atoms, and the final state, H2, are mirror symmetric. Right, so here's a maths problem for you. Right, this is a symmetric function, this is a symmetric function, this is an antisymmetric function. If I multiply these 3 together, is the result symmetric or antisymmetric? Antisymmetric. Whoever said that gets chocolate.
Who said that?
There you go. All right. Here's practically. I integrate an antisymmetric function over all space. What is the integral? 0. Give that man a chocolate. All right. You can just read here. But yeah. So to first order, to leading order, you cannot emit or absorb photons if these are your initial and final states. Now, this is to leading order. There's a perturbation term, right? These states are not exactly perfectly symmetric due to spin-orbit coupling, but the amount by which the symmetry gets broken is of order alpha squared in this term and alpha squared in this term. So this matrix element winds up being of order alpha to the 4th, which is a very small number. So small that in practice, this never occurs. So the implications here are, first, it's nearly impossible to form H2 in the gas phase, because you think, well, all right, I take 2 hydrogen atoms, I ram them together, I emit a photon to get rid of the binding energy, but I can't emit a photon. And so I can't get rid of the binding energy, and so I can't form H2 in the gas phase. Conversely, you might think, well, all right, 4.5 eV, I could use a 5 eV photon, like a visible light photon, and dissociate H2, but that won't work either, because the H2 won't be able to absorb it for the same reason. All right, so this is the key constraint that governs all of how H2 forms and dies. All right, so how do you form H2 given this? Right, the problem is I need to get rid of the binding energy, right? If I have 2 free hydrogen atoms and I want to go to an H2 molecule, I have to put the 4.5 eV somewhere. So where do I put it? Well, the answer is I put it on a dust grain. So I can have hydrogen atoms that will stick to a dust grain. If I have 2 hydrogen atoms stuck to the surface of a dust grain and they find each other, well, then I have a place to stick the 4.5 eV. I can put it into the vibrational lattice of the dust grain. All right, and this is overwhelmingly the way that H2 forms in the modern universe. Now, there are other pathways that let it form in primordial star formation, and I think we'll hear more about that later in the week. But in the modern universe, this is overwhelmingly the way H2 forms, is catalyzed on the surfaces of interstellar grains. So as a result, the formation rate is proportional to the dust abundance, which just scales as, total number density times dust to gas ratio, times the free hydrogen abundance. So you can write this as some rate coefficient R, which is proportional to the metallicity, or the dust to gas ratio, times the total number density times the number density of free hydrogen. And in the solar neighborhood, this R has about this numerical value. All right, so that's how H2 forms. How does it die? All right, well, to answer that, we have to look at the level of astrochemistry. Let me walk you through this plot. All right, so A here is not AU, it's atomic units. So this is a plot of the potential energy of the internuclear separation of two protons. All right, and you have different electronic states. This red line corresponds to the ground electronic state. These other colored lines correspond to the various higher electronic states. All right, now, if you remember back to my lecture on Monday, for each electronic state, you then have rotational and vibrational substates. So within each of these electronic states, you have the V equals 0, the V equals 1, the V equals 2, the various vibrational states. And then within each of those vibrational states, you have the various rotational states, the J states. All right, so how do I destroy an H2 molecule? Right, the problem is I can't go from, say, here, that's the bound state, to here, the unbound free state, by absorbing a photon, because this is symmetric and this is symmetric, and symmetry tells us that the electric dipole operator vanishes. So I can't go from here directly to here, but I am allowed to go from here to here, and that's because this is not a symmetric state. Right, here, one of the hydrogens is in a different state than the other. So this is an asymmetric state, so is this. And that means the electric dipole operator doesn't vanish, and I can therefore do this transition. All right, so if I start with my H2 molecules that are in the ground state, and I hit them with high enough energy photons, I can promote them to these excited electronic states. Now, the minimum energy required to do that's 11.2 eV, right? That's where the minimum of this green curve. So I need to use ultraviolet photons. I can't do this with visible photons. I have to do it with ultraviolet photons. I need a minimum of 11.2 eV. All right, and you might think, well, why, so I should get some lines, right? I should get a line from transitioning from here to here. And yes and no. I do get a line. I don't just get one. Because for each of these V and J states, right, there's an initial V and J state. So even if I start with everything in the V equals 0, J equals 0, all right, there's an infinite number of V and J states associated with this electronic state too, that are all at slightly different energies. And I've got a finite transition rate to each of those. And so rather than getting a single line, I get a forest of closely spaced lines, an infinite number of them, connecting the infinity of V and J states here to the infinity of V. All right, so we call that a band rather than a line. The transitions from the ground electronic state to the first excited state are the Lyman band. The transitions to the second excited state are the Werner band. All right, now, how does that help me destroy an H2 molecule? Well, just like because this is asymmetric, I can go from here to here. Because this is asymmetric, I can also go from here to here. So I excite, and then this excited state will spontaneously de-excite. Now, it could drop back into the bound state, but it's also free to drop back into the unbound state. All right, energetically, that's perfectly allowed. And it turns out, depending on exactly which VJ I'm in, the probability of that happening is sort of 10 to 15%. All right, so for every roughly 10 UV photons I absorb that excite me into this state, 1 in 10 of those molecules, when it de-excites, will unbind. And that's how I destroy H2. So here's my question. I focused on the first two excited electronic states, and I mentioned the first two, the Lyman and Werner. Right, there are other states. Why didn't I talk about the third and the fourth and the fifth? I'll put the diagram back up, because the answer can be found by looking at it. Why am I only concerned with the first two electronic states? Yep, give that man a chocolate. All right, the basic reason is the following, right? I mean, to get to this third excited state, right, I need a photon that's more than 13.6 eV. And I never have photons at that energy. Right, the ISM is a brick wall to 13.6 EV photons because there's so much hydrogen and the cross-section is so large. So I don't have a supply of 13.6 EV photons. If I did, if I had, 14 EV photons, they could destroy H2 molecules too. But in practice in the ISM, unless I'm inside an H2 region, in which case I have no H2 molecules, yes, that's terrible, I know, right, then I don't have any 13.6 or more EV photons to work with. So the only levels that are relevant are these two, because those are the ones that it's possible to excite using photons with energies less than 13.6 EV. All right, so here's a simple way of thinking about this. All right, now this is a huge oversimplification. In real life, you have to worry about dust and complicated radiative transfer effects, but it turns out you can get the first order answer in 2 slides, and that's what I'm going to do. So here's the first order answer. Let's consider the dumbest possible setup. I have a slab of gas, and I shine Lyman-Werner band photons on it. So the color is the H1 fraction. So blue is mostly H1, and as I go further in and these photons get absorbed, it transitions to mostly H2. You didn't know that H1 was blue and H2 was yellow? Oops. I thought you'd have known that. Yeah. So this is the basic setup we're going to consider. We're going to have a slab of gas. We shine Lyman-Werner band photons on it. At the surface, I've got lots and lots of photons capable of destroying H2 molecules. So the equilibrium chemical state is going to be almost entirely H1. But as I go into this slab, I'm using up more and more of these photons. And eventually, I've used up so many of them that the dominant chemical state switches to H2. All right, and I can solve this problem as follows. I say, all right, let's let phi be the Lyman-Werner photon flux, just expressed as, photons per square centimeter per second. All right, and I say, let me consider some slice of thickness dx. All right, and if this material in here is not entirely H2, then there'll be some rate at which H2 forms. The number of H2 molecules that form per unit time per unit area, well, is just n times nh times this rate coefficient times dx in this slab. All right, and in chemical equilibrium, dissociations and formations have to balance, and the dissociation rate is this F dissociation times the change in flux, right? How many photons got absorbed, and then 1/10 of those absorptions lead to a dissociation. All right, so I say that this equals this, and I get an ODE that I can solve. All right, so this is an ODE. It's subject to the boundary condition that there's some initial flux phi naught at the surface, and I can integrate through the cloud and find where do all the photons get used up, and that's where the transition from H1 to H2 occurs. All right, so you can do that problem. It's a very simple ODE, and you can solve it numerically if you want, but in fact, you can solve it analytically in the limit where you approximate that the transition from H1 to H2 is sharp, which is not a terrible approximation. All right, and you find that the column of H1 you have to go through before you make the transition to H2 is given by this expression. All right, so F dis times this phi naught divided by NR. Now, it turns out that this phi naught over n is about constant for reasons I won't have time to go into. But you can also just plug in typical Milky Way values. And this rate coefficient we know. And so you can just read off what is the column at which I expect to transition from H1 to H2. Turns out to be about 10 to the 21 at solar metallicity, or in terms of mass surface density, about 10 solar masses per square parsec. This is why molecular clouds live above 10 solar masses per square parsec. This is the fundamental reason right there. All right, Moreover, there's a clear prediction here, which is that because this rate coefficient is linearly proportional to the dust abundance, which should scale like metallicity, this column should scale inversely with metallicity. And that's in fact exactly what you observe. All right, so this plot from Shrub et al. Is showing this is total gas surface density versus just H1 surface density in nearby galaxies, and the lines are just different metallicities. All right, and what you see is these all show a pattern where at low surface density it's all H1, and then the curve turns over and flattens, and that's because once you've accumulated this shielding column, any additional gas you add will wind up being in the form of H2 rather than H1. So that's what gives rise to this characteristic. It moves along the one-to-one line here, and then it turns over and goes flat. But you can see that the value at which it goes flat is inversely proportional to the metallicity, which is exactly what you expect. All right, so this is what governs H2 formation and destruction. So now we know how to form a molecular cloud. You need to accumulate 10 to the 21 hydrogens per square centimeter or 10 solar masses per square parsec. Great, that's the first order answer. Let's move on. Let's talk about once you've formed, yes? Sorry, go on.
Molecular component, right? Sorry, maybe I just missed something.
Yes, well, I mean, this is for solar metallicity. You accumulate, 10 to the 21 over Z. You accumulate this column.
Yeah, okay.
Right, so in the limit where there's no dust, this number goes to infinity. Right, you'd need to accumulate an infinitely big column if there were no dust.
Right, okay.
Of course, in reality, it's not infinitely big because, other processes become important in the zero metallicity case. But this is what happens near solar metallicity. Is that good? All right, so we formed a cloud. We've accumulated enough gas. How long does it live? All right, well, let's start with, we can say that we know what the answer has to be in some sort of average sense. And the way we know that is that we know the Milky Way's star formation rate is of order solar mass per year, a couple solar masses a year. And we know that in the Milky Way, we have about 10 to the 9 solar masses worth of GMCs. All right, so you can immediately say that the depletion time averaged over all clouds has to be of order a gigayear. Right, that is, if you've got 10 to the 9 solar masses worth of gas, and on average you're forming stars at a rate of 1 solar mass per year, the time to use up all that gas, the depletion time, is a gigayear. But of course, that's a whole galaxy average. That doesn't prove that individual clouds live that long, nor does it prove that it's the same from one cloud to another. So how do we measure the lifetime of GMCs? Right, and this is fundamentally hard. You could just wait and watch, but modern PhD students are lazy and are not willing to wait a gigayear to get their PhDs. Lazy. All right, and the fundamental problem we have is that there are no intrinsic clocks in GMCs, right? I show you a cloud of gas. How old is it? How do you know? There are actually chemical clocks people try and use, but it's hard. All right, so the fundamental trick we use is we say, well, all right, clouds don't have clocks, but stars do. Right? If we know something about stellar evolution, then we can look at stars or population of stars and make some guess about how old it is. So we use the stars as our clocks to time the gas using the correlation between the two. So here's the basic cartoon picture. All right, and this is something that Diederik Krausen and Steve Longmore developed over a sort of decade. I'm going to give you the cartoon version of it. So here's the cartoon version. We've seen something like this before. Nuria showed it, right? So our cartoon version is that you form a GMC and you've got a phase where there's just gas and no stars. Then there's an overlap phase where there's gas and there's embedded massive stars. And then you disperse the cloud and there's a phase of just stars. All right, and the trick is, if I have a bunch of gas and stars and I just measure the average in some very big aperture, right? I average over the whole galaxy. Well, that gives me the average depletion time. But I can then envision taking smaller and smaller apertures. And as I do that, I won't sample over all possible states in this evolutionary cycle, right? Some of my apertures may wind up having just this phase. Some of my apertures will wind up having mostly this phase. All right, and you can ask, well, all right, if I compute the depletion time within an aperture, or maybe not the depletion time, should think about it as simply the ratio of whatever my tracer of gas is to whatever my tracer of star formation is, right? If I happen to catch mostly gas peaks, well then it will look like there's a very long depletion time. If I happen to catch mostly stars, it'll look like a very short depletion time. And so, as I change my aperture, I get what's called the tuning fork diagram. And the shape of this tuning fork is sensitive to how long molecular clouds live. All right, so here's the sort of statistical method you can use. All right, so the time for which star clusters are on is set by stellar evolution, right? I know that, like, once I form massive stars, I will get ionizing photon emission 4 or 5 megayears after that, because that's how long massive stars live. That's my absolute time scale. So I know that the entire duration for which I see H alpha emission should be about 5 megayears. All right, and then I say, well, as the gas lifetime, the gas-free lifetime, or excuse me, the gas only with no star formation lifetime gets longer relative to this, well then it should be more common to find gas peaks relative to star clusters. So apertures that are focused on star clusters must show a smaller depletion time relative to the mean of the galaxy in order to compensate for the large number of gas clouds that have no stars. All right, so the way this shows up is that if I plot this B parameter, which is simply the depletion time measured in my small aperture to the galactic average, as I make the gas lifetime longer, as I go from red to blue here, all right, this tuning fork opens up wider. All right, and different aspects of the shape of the tuning fork are sensitive to different aspects of the cloud lifetime. But you can use the shape of this tuning fork to deduce molecular cloud lifetimes. All right, and if you do that, and this is Melanie Chavance's work, so you can do this on maps of nearby galaxies like these, and you get a bunch of these tuning forks, and you can, from each of these, read off things like the molecular cloud lifetime. All right, and if you do that, and I'll just skip to the punchline, you get results that look like this. So how long do molecular clouds live? 20, 30 million years. All right, now notice that this overlap phase in red here is very short. It's only a few million years, and this means the interpretation is molecular clouds, once you've started forming a lot of massive stars, they disperse quite quickly. Now, this lifetime is, you know, significantly longer than a free fall time. It's a few free fall times. So molecular clouds are in this sort of awkward intermediate regime, right? They don't live just one crossing time or one free fall time, but they also don't live for like 10. They live an intermediate amount of time. Now, one thing that you may notice is this is a little awkward to fit with what we see in the galaxy, right? Because we supposedly have this long gas-free or star formation-free phase where it's all gas. But if you look in the galaxy, you never see GMCs that have no embedded stars. Those basically don't exist. So probably the answer has to do with the fact that this is massive stars, right? This has to be, to show up as red here, you have to be emitting enough H alpha tension there. And a second bit of tension I should mention is that there's an entirely orthogonal way of trying to get at cloud lifetimes, which is to use stellar kinematics. All right, this is something that's become possible in the age of Gaia, is to find stars and then, using your 6D knowledge of their velocities, you can only do this with stars where you also have spectroscopic information, so you get the radial velocity. You've got big enough samples of those that you can start to trace them back in time. All right, so this is work from like Ronan Kerr, showing the stellar trace back for the austral complex. All right, so this is showing the sort of formation history of the austral complex to the present day. Each of these stars is, you know, sort of a different group. Now, what I want you to notice about this is not so much like, you know, the pattern, although motion, although it's cool. It's the clock. It's that. Stellar kinematically, you can trace this complex's history back at least 50 million years. Right, so there's been some sort of coherent pattern of star formation producing the stars in this complex over at least a 50 million year time scale. So even though, you know, this technique just told us molecular clouds live 20, 30 million years, from the stellar kinematics, we see coherent patterns of star formation that persist somehow for at least 50 million years. Now, how to put this together with what you're getting from the sort of statistical I'd say is an open question, yes.
Maybe it's just the way they plot it, but just you start randomly to get a lot of stars? Is it just, and you go back in time, so did these stars explode, or how do you have like how, because we just get random stars in this plot while we're going back in time, and especially around like minus 45 or something.
Well, I mean, I think it's not random. I think it's, that stars are forming. So I think their interpretation would be that this is a complex that's sort of assembling. So if we go back to, wait for it to loop over, right? So you've got sort of the early stars. A bunch of stars form in sort of a burst there. All right, and you have, sort of stuff drifting and moving, and then you get, additional bursts of star formation later on. There's another little burst. Well, this is, so the times are I think are from the isochrones, right? These are individual stars where you can put them on an HR diagram. So they know the ages. Yes. Yeah.
How big it was when it
Yeah,
goes
so I mean,
back
this is a big
to time zero?
Yeah, I mean, this is a big complex. So this is, this is order 100 parsec scale. So this is a big complex. It's like a 100 parsec complex.
So in a sense, I mean, there is like a coherent time scale, right? The star formation is out.
Maybe so. That yes. And so the question, I think, is how do you put this time scale that there's some coherence over 100 parsec time scales for 50 million years together with the, 20 million years you're getting from the uncertainty principle analysis? I think that's an open question. Right, it is, but I mean, they've done this analysis on two complexes, and for both of them, the time is longer than 20 million years, so yes.
Sorry, yeah. I don't see such a big problem here because, I mean, it's a couple of tens of million years. I remember my first astrophysics lectures. It was Ralph Bender always insisted on the fundamental law of astronomy, which was 2 = 1.
Right.
And according to the fundamental law of astrophysics, this is completely consistent.
Fair enough. On the other hand, there are a lot of people who'd be very upset with a 50 million year GMC lifetime. So I don't think it's a huge problem, but I just wanted to mention it. All right, let me go on because I'm running short on time. So all right, that's sort of lifetimes. What about depletion times, right? So again, the depletion time is defined as gas mass divided by star formation rate. And a natural thing you can define is the ratio of the freefall time to the depletion time, which is this quantity epsilon FF. It's the fraction of the mass converted to stars per freefall time. And in some ways, this is the fundamental number for star formation, right? This is the dimensionless measure of how efficiently stars are forming. All right, so we know, as I already mentioned, if you average over the entire Milky Way, this is a small number, right? The star formation rate is of order of solar mass per year. The depletion time is order a giga-year. So if you say that the free fall time is maybe 1 mega-year, then, or excuse me, I think that should be 10 mega-years, then epsilon FF is 1%. Right, so that's the average over the whole galaxy. But of course, that doesn't tell you what it is in an individual cloud. Right, you could certainly arrange to have this average come out right by having, for example, 99% of your clouds don't form any stars at all, and 1% have come out right. So how does epsilon FF vary from cloud to cloud? Scattered, or is it all the same? Right, now this is not so easy to investigate due to timescale issues, right? So for example, because molecular cloud lifetimes aren't that long, you can't just use tracers like H alpha or infrared and assume they'll reliably give you the star formation rate. This goes back to this point I made on the first lecture that, right, if you want to use a tracer like in H alpha or infrared, you have to have been confident that the star formation rate has been constant for of order 10 million years, which is a totally reasonable assumption when you average over a whole galaxy, and a totally unreasonable assumption when you look at an individual molecular cloud. All right, so what do you do? Well, probably the best way of getting around this is to work on clouds that are close enough You can just count the damn stars. All right, so you can do this in very nearby molecular clouds, like, this example is MON-R2. So here's a dust map from Herschel, and then all these little pink stars are little pink stars. They actually look sort of pink if you choose the right color scale. These are individual protostars. All right, and they are class 0-1 objects, so we think they live order 500,000 years. So now you have a much more sensitive short timescale tracer. To first order, your estimate of the star formation rate is simply however many of these there are multiplied by the average stellar mass, order of solar mass, divided by 500,000 years. That's obviously not right at better than the factor of 2 level, but that's fine. So what you can do is you can get star formation rates this way, and then you can get gas masses by, say, drawing a contour. So you draw this contour, you add up the mass within it, you add up the stars within it, you have a mass, you have a star formation rate. You know the mass within the contour and the area, so you can at least make a guess at the density and therefore the free fall time, and you get an epsilon FF. And you can do that for every contour, and you get plots like this. All right, so what do you do? So what do you get? The answer is epsilon FF in each of these clouds you can try this in is all about 1%. Look at individual pixels in nearby galaxies. All right, these are sort of much larger scales. These are 150 parsec scales. And look at the distribution of epsilon FFs. And again, it's fairly narrow. The scatter is, a factor of 2-ish. So it isn't the case that the way we achieve the 1% average over the galaxy is by having a bunch of clouds that have 100% star formation efficiency and a bunch that have 0. It's that the variation cloud to cloud is only at the factor of 2 level. Every individual cloud seems to have epsilon FF of about 1%. Oh, and I'm reaching. So all right, here's my last slide. So what kills off molecular clouds? What ends this cycle? Well, Maya already mostly answered this, right? You can come up with external forces like galactic shear or tides, and that might be important in places like the galactic center where you have very strong tidal forces. But it's not going to be very effective out in the disk where the tides aren't that strong. Maybe it's important for limiting the rate at which molecular clouds assemble in the first place. But once they assemble, it's not going to tear them apart. So instead, it's probably some form of stellar feedback. All right, photoionization, radiation pressure, stellar winds and supernovae. And again, Maya covered this, so I won't talk more about it. What I will simply note is that because you now know that cloud, and we saw that the lifetime is about 5 free fall times, something like that, this implies that the star formation efficiency on a cloud-by-cloud basis is of order of 5%. All right, typical molecular cloud turns 5% of its mass into stars, and that 5% is then sufficient to unbind the rest. So that's an important constraint on models of feedback, which is that you have to do it without using up much of the mass, right? Feedback has to be efficient enough that you can take 5% of the gas mass and put it into stars, and that 5% has to be able to kill the remaining 95%, which is an interesting constraint on feedback. All right, and I think I will end up there a little early. Questions? Yeah.
When you say kill, is that gas is not in the H2 phase anymore, or is it just that entity, which we think is maybe gravitationally bound or marginally gravitationally bound, doesn't exist anymore, but H2 is there in a non-bound phase? Do you understand the...
Yeah, no, that's an excellent question. So I didn't put this in, but in fact, so Sarah Jefferson led a paper with Vadim Semenov and me on exactly this question, which is on the archive. And our so the question, the way we thought of the question is, let's distinguish between the Eulerian and the Lagrangian lifetimes of clouds, right? So the Eulerian lifetime is how long is this coherent structure here. The Lagrangian lifetime is how long does an individual fluid element spend in, say, NH2 dominated state? right, and spend within this structure. And you could envision, you know, as you said, you could envision that you destroy clouds, but for example, nothing ever leaves the H2 phase. So you could envision that, you know, you're always molecular, and it's just, you know, you spend some time in a cloud, some time out of a cloud and unbound. That's one possible scenario you could envision. You could envision the opposite scenario where the cloud, you know, lasts much longer than any individual fluid element, because fluid elements come in, and spends molecular and inside the cloud is much shorter than the time for which the cloud in an Eulerian sense lives. So we did a bunch of simulation dynamics, and our conclusion was it's the second one I talked about. So the destruction is mostly that you're kicking fluid elements out of clouds, but at least for massive clouds. And this, I think, may be the answer to the thing I showed with the traceback. The cloud lasts longer than any individual fluid element within it. So the picture we're driven to is that a molecular cloud is a lake, right? The lake is defined by there's a minimum of the potential that attracts water. Any individual water molecule spends much less time in the lake than the time for which the lake exists. Water flows in, water flows out. The lake is a persistent feature, but individual water molecules don't spend that much time in it. They spend maybe only a couple weeks. Right. So no, so what we find is no, it actually doesn't remain H2 that long. So yeah, so it comes into the cloud, turns into H2, gets thrown out and dissociates, and so the average, if you trace a Lagrangian fluid element, the average amount of time for which it remains in an H2-dominated state is only about 5 million years, even in a cloud that lives 50 million years. And it's simply that, you know, you go through 10 generations of this stuff over the course of the cloud's lifetime. So that's what comes out of our simulations. Other questions?
Or whatever that you alluded to.
Yeah.
And if you're bringing in, you're constantly accreting, quote,
Yep.
fresh material and whatnot.
Absolutely, yes. It has an implication that stuff should always be chemically young, because the Lagrangian lifetime of a particular H2 molecule is never, you know, individual H2 molecules do not live to a ripe old age.
Yes, I was wondering about one thing that you mentioned really briefly,
Yeah.
but I would like if you can go deeply, which is about the question, what happens, like, let's go to the very early phases of the universe.
Mm-hmm.
There is some molecular clouds collapse.
Yes. Yeah, that's fine. I can hear you, yeah.
So, which is these other mechanisms that are helping in the H2 early formation and where they become dominant? There is like a specific threshold for these
Yep.
mechanisms to, because if there is also pre-spin gas
Yep.
into galaxies, we should expect to see this also formation of H2 at some point.
Yes. All right. So I'll repeat the question for anyone who's watching on Zoom, since the mic died. The question was, all right, well, H2 formation is totally dominated by dust grains in the early universe, or in the modern universe. That clearly can't have been true back to zero metallicity when there were no dust grains. So what are the other formation pathways that can exist when there aren't dust grains, and where's the transition between those two? Is that a fair summary of your question? All right, so let's only take the first question. The first part is, how do you form H2 without dust? And the answer is there are two main routes. All right, one is electron catalysis. So if you have something that can generate free electrons, all right, and that could be cosmic rays, it could be ionizing photons from the next halo over, anything that generates free electrons. Well, free electrons can play the same role as dust grains. That is, you can have a hydrogen atom that can bond with a free electron to form H minus. H minus is a bound molecule. And then the H minus then hits another hydrogen atom. That can react to form H2, kick out the electron, and the electron carries away the bonding energy. This is not an efficient process because it's limited both by the supply of free electrons, which is not a lot, and by the fact that H minus is very fragile, easily photodissociated. So most of the time H minus won't, it'll die by being photodissociated. Not an efficient route, but that's what you've got in the early universe. The second route is that if you get to very high densities, like 10 to the 12, 10 to the 13, you can have three-body reactions where you have three hydrogen atoms that sort of all collide simultaneously, and then two of them become bound and the third one gets kicked out and carries away the binding energy. Since it's a three-body reaction, it requires very high density to occur at any appreciable rate. All right, so that's how you can do it. Now, as the question, when do you transition between the two? Depends a little bit on the supply of free electrons, but generally speaking, even at 1% solar metallicity, even below that, grain catalysis wins. You have to go to really low metallicity for the H- channel to be competitive with grain catalysis. So no modern galaxy has a metallicity low enough that it isn't dominated by grains. You have to go to really low.
I think we've got one final question, Mark.
So if I remember correctly, you showed the galactic average epsilon FF is 1%, and also the epsilon FF measure for each STARFORM region is also similar to 1%. So does it mean that all the GMCs in the galaxies eventually end up forming stars? Because otherwise, the galactic average should be lower than that.
Yeah, I mean, it's certainly the great majority of them, yes. I don't think we have any significant mass in inert GMCs that never make any stars. I mean, if you told me that, there's a 10% of the population, obviously I can't rule that out. But yes, I think it is a fair conclusion. There cannot be a dominant or even, order unity component of GMCs that never form any stars.
All right, in the interest of time, let's thank Mark.
All right, thank you.
Next we have Maya. Not Melanie.
Do you want to use my dongle or do you need it?
No, I'm good. Thanks. I think I'll get the stick. All right. So hello again. I am Maya, still not Melanie. I have a very privileged position right now to give you a talk which is both in the middle of this school in terms of time frame and also very much at this transitional point in terms of scales. Because up until now, we've been talking about what is mostly on the smaller scales and mostly within our galaxy. And right after the coffee break, we are actually stepping to the larger scales, and then we're going to start talking about galaxies and things like that. So I thought this would be a great opportunity to talk a little bit about scales. And here I've put quite a broad range of scales. And the reason that we have to consider all of these scales is that they're all important for star formation. So matter really likes to self-organize into structures. And so starting from the absolute biggest scales that me as a galactic person can imagine, so something with actual clusters of galaxies, we have structures, and then we have substructures and substructures, and this cascades down. And I'm going to make my provocative statement of, I believe that one of the main reasons we haven't solved star formation yet, and the reason why we need to have schools like this one, is because we have all of these scales which are interconnected, and they all matter for the process of star formation. Now, this is not the only reason. We also have a lot of very complex physics, so it's not quite such a clean-cut picture. But I would argue that the fact that we have many, many, many orders of magnitude that are all important for the star formation process is right up there in terms of importance. So, as I said, matter likes to organize itself. So starting from the biggest structures, kind of going downwards because of gravity. So if we think about it, on the largest scales that we have, we're going to have some variation between the galaxies that exist, based on where they are exactly in their galaxy cluster, based on their evolution. So we could have variations of mass between different galaxies just because of how they happen to come to be. We can have variations in gas content and metallicity, in accretion history, and we would imagine that these three scenarios, for example, are going to have a very different star formation process, like when we zoom down in the levels and cascade down. But then even if we were just to pick a galaxy like this one, for example, that would be something similar-ish to the Milky Way, then even in the sub-galactic scales, when we start looking at the clouds, they're going to have different properties based on where they are in the galaxy. A simple example, we already saw this figure several times in the last couple of days, but this figure shows in blue clouds in the outer galaxy, and in orange clouds in the inner galaxy. And we can see actually that the inner galaxy has clouds that are a bit more massive and they have higher densities. And this is not the only type of variation that we can find in clouds, but this gives us an idea that if you are a star that is forming in the inner galaxy, you might have a different experience of this process compared to a star that's forming somewhere else. And then the more and more we zoom in, we see more and more substructure. We've been talking about filaments in the last couple of days. And yes, we also touched on the fact that with these filaments, you could have different masses contained in them. You can have filament structures where material is funneled in. And of course, in an environment where you might have a large concentration of mass, you might have a very different star formation process compared to something that is kind of more isolated somewhere in the outskirts of the clouds, where not much material is flowing towards. And then the more and more we zoom in, we get to the fact that not every star has the same mass. The fact that we have an actual distribution of stellar masses means that not every stellar core is going to end up with the same mass. So it's going to undergo a slightly different process, leading to a mass, to a star with a different mass. So in a way, even if we start from these larger scales, they're going to have some influence all the way down to the tiniest ones. But then another way in which the scales are related is through the influence of feedback, as I talked about yesterday. So you could have feedback that starts from the smallest scales. By the way, all of these images, still images of feedback. So starting from the smallest scales, with this jet here and etc., we can have feedback processes that are then affecting the scales above them. So we can have the ionization and winds that I was talking about yesterday that can impact both GMC scales and galactic scales. And we also have the supernovae, which of course contribute to the full galaxy, but then they are also related to galactic outflows. So material is even leaving the galaxy. We're going to even larger scales. So everything is interconnected, and this makes it quite complex. And the way we go about trying to study this is we kind of try to attack the problem from both sides. So on the small scales, we have Milky Way studies where we could really see individual star-forming cores. We could see all of these things leading up to about GMCs, because we can't really see our galaxy in the highest level of detail that we wish we could because of limitations. And then from the extragalactic side, we've been able to resolve smaller and smaller scales. And again, we're kind of converging towards GMCs. So this is really like the bridging scale in that sense. So I would say that this GMC scale would be the largest scale in which we can still resolve individual star formation in the Milky Way, and maybe in some of the nearby dwarf galaxies, maybe not exclusively in the Milky Way. But at the same time, it's the smallest scale that we could realistically resolve, at least for the nearby galaxies. Of course, once we go further away, that becomes prohibitive again. And Nuria actually illustrated this beautifully in her talk by comparing what is now a very, very highly resolved region, cloud region in an external galaxy versus a similarly sized region in the Milky Way. So it is, we still have some distance to go until these two pictures start looking the same, but we are slowly converging towards this scale and trying to kind of link everything right about here. Interestingly, this is also in a way mirrored in simulations. So if you have simulations like this one that I showed you a video of yesterday of an individual star-forming cloud, if it's not a very, very massive one, then we could actually resolve individual star formation if we kind of push to the limit a little bit. And then when we start simulating entire galaxies, then we have very similarly blobby picture on the other side. Of course, one could argue maybe we could improve this resolution a little bit, but we will not be able to resolve individual stars if we can also model the entire galaxy, let alone galaxies that exist in cosmological context. So in simulations, we really have similar kind of restriction, and this really has to do with dynamic range. It's just such a huge dynamic range problem. We can't solve it from the largest to the smallest scales or from the smallest to the largest scales at this point in time. Yes, another note on the GMC scales. This is kind of a natural scale to produce cluster star formation, and there is clustering, of course, on the subscales as well. We talked about multiplicity yesterday, and yeah, but maybe birthplace of stellar clusters. We haven't really touched on this yet. Might be an interesting, or we touched on this yet, but maybe not in full depth. Okay, and as I said, we are now halfway through the school. This is the bit that we've covered. This is the bit that we're transitioning towards. And the fact that star formation is such a diverse process means that, first of all, as I said, we have to cover all of these scales, but also we have to bring people with expertise on all of these scales in the same room in order to really talk about this problem comprehensively. And we should, in fact, talk to each other, because since all of these scales and processes are interconnected, it is important that we actually communicate in the same manner. And to take a cautionary tale out of what Mark said in his, I believe, his first talk, with those optical and radio astronomers who never talk to each other, and that led to very, very confusing multiple naming conventions for star forming cores. Yeah, we should, in fact, try to avoid this by communicating with each other more and really leaning into the expertise that we have in this room. So, on that note, we are now going to talk to each other. So, I would like you to find a person in this room, preferably one that you haven't talked to yet. I'm sure that not everybody has had the chance to talk to everybody else. And ideally, this person should be working on different scale, topic, physics, etc. from you. That shouldn't be too difficult. There should be quite a big spread here, I would imagine. And yeah, I want you to have a chat with them about what you're both interested in and what kind of questions that you have. And once you formulate one or many questions, they should come here on this board. We have a lot of these sticky notes. I'm gonna distribute the sticky notes, and then we can, yeah, I'll open these.
Yeah. What time do you want to give people to do this?
10 minutes.
10 minutes?
Yeah.
All right. 10 minutes. What are the big questions?
small scale. There you go. There you go.
So what's the plan after this? We're going to put everything on there.
Yes.
And then do we have, how do we collate?
So I was thinking then I will ask somebody to volunteer what their question was, and we put it up, and we started having some discussions.
What is your opinion? What's like the next question? What is the question that most interests you?
Yeah, exactly. Yeah, and we just try to have a discussion. That's the plan.
You're freestyling.
There you go.
Oh, okay. An opportunity to go to the bathroom though.
Yeah.
So I can't say who's going to change it, right?
Yeah, they're talking.
It's a success, if nothing else. I think what we should do is like go around the room and ask these questions and sort of find out. But yeah, ultimately stick it in at the end and then we get to them and then that can be used for discussion.
Exactly. I was trying to.
Between now and Friday, we could like go and see if there's any groups of questions that like connect together.
Exactly. I was also thinking maybe it will turn out that we overlook the topic that maybe going to. So, first question.
Yeah. You're going to make me run around as well, aren't you? You're going to need lots of chocolate.
Yeah, I think I'm not gonna give them chocolate for sticking the question because everybody should do this. But like once they share, yeah.
I agree.
But I'm gonna let them talk for as long as the question. Yeah, because it seems like they're.
I will just follow your lead, Maya.
Okay. Yeah,
Have you got other slides that you go through at the end? Or is it just
I have like a question slide where I wrote a couple of questions, but I'm gonna actually type up the questions as they call them out, so that I have a written record at least of what was discussed. Yeah.
yeah, go for it.
We could just put it here. It's fine. I yeah, I think we will pull everybody together and see if we can start some discussion. That was kind of my thought.
Just so there was a galactic center on there, so I can point to the talk tomorrow. And
Yeah.
so,
Yeah, perfect. I mean, some questions maybe that are relevant to the topics that have already been. Yeah. Did you have a question? It was kind of more rushed. Okay, so there's still many people who have not put. I was trying to gauge at what point do they just start talking about, their lunch plans. But maybe the number of notes should be an indicator. We're still expecting more.
We have a doubt. define inner and outer galaxy, and apparently they do not say this in their article. So they separate where the sun is.
I actually
Have you
don't
anything in
know.
your head, or if not, we just keep on continuing?
I don't know how they.
The galaxy and Z. We've been looking at the
I mean, the entire article how they define inner and outer galaxy. I mean, probably the most logical thing is that they take the sun, and then inside the sun and outside the sun.
maybe. Have you done a
That's a quite interesting thing to find out.
have you done a control F for galactic center or CNZ?
I've done a control F for outer.
Yeah. Okay. All right. Interesting.
Anyone in the room who is on that paper? They don't use the CMC, in fact, because if you look at what was it, figure 10?
Yeah.
Oh, yeah, okay.
Look at figure 10, the CMZ for them does not really exist.
Yeah. Okay.
Yeah.
Too confused. I don't know.
Yeah. I'll give them a reminder now. So, guys, hopefully you're starting to converge towards some questions. I'll give you like a few more minutes. Please write down what you have already and just put it up. Okay.
Should debate altogether that you had on the slides. You said, so far we have not been solving star formation. What do you mean by solving star formation? No, but I think it's very. When would you consider star formation to be solved? You know, as a.
We understand everything about it.
Well, but you know, as the more we understand, of course, the finer become the.
Yes, I agree. Provocative one.
No, I know. I think it's. You're going into the philosophy. No, but I think it's. For students, it's interesting, you know, to debate these questions because at the end of the day, the reasons, you know, why we are doing our science, what are we taking for?
I was collecting questions from people for discussion. So I will actually put yours as the first question.
All right,
Yeah,
okay.
yeah. Okay, are we more or less happy? Are you guys still writing up some questions, or are we more or less done with this part? More done? Yes, more yellow papers are coming. But more or less done. Okay. You can always add more questions. Just so you know, like this is not your last opportunity. But in fact, please do keep adding questions because that's really the only way that we're going to get to answer them. If we don't know what your questions are, we're like, the odds are significantly lower that we will address your exact question. I'll wait for you to finish writing. And then we can go on. Okay, so I assume that we're good to go now? Yes. Yes. Okay, excellent. Thank you all so much for putting in all this effort. We now have a lot of questions. Oh, one more.
But maybe one is misleading, so my bad.
Very prolific. I am very pleased with this. Excellent. This is exactly what we want. So now that you've put all of this effort to write down your wonderful questions that we will look over, would anyone like to share with all of us what they wrote as a question? The point now is to actually have a discussion about some of these questions. So, like to share their question with us?
Okay, yeah, I already got a lot. I'm gonna get diabetes for that. Anyway, so yeah, I do simulations, so obviously I think in the simulation box. Yes, I think in the box. Sorry, I know it's mostly observers here. So what we do with typically small-scale cloud scales is that we have the spherical or whatever cloud of gas that sits in a box that probably doesn't have any background in it, no medium in it. It's literally in the middle of nowhere. And it would simply evolve it to let it collapse and form the sinks and to look at the star formation. But obviously from what Marx has just talked about is that obviously the gas should be coming out from the outside galactic environment and deposit onto the cloud. And if we're looking into the Lagrangian fluid parcels view, that they should actually, well, they don't sit in the cloud for all that time, and they should be coming out from the outside and sit there for a bit of time, and at some point they should leave. But we never consider this kind of process in small-scale simulations because we will just have that same bunch of particles or same bunch of cells, whatever if it's a particle or grid or whatever. But it's the same thing. We never simulate that in and out, nor we have streams. I also heard from Ian Monell that we should try also consider having some streams, some incoming streams into the cloud, but how that's done in the simulations, that I'm not completely sure. So yeah, would that be something worth talking about? How streams should come from the outside to the small cell clouds in the simulations? Maybe from an observer's point of view, how should that happen?
So to maybe paraphrase your question to how would we link simulations on different size scales? Okay. Yeah, we could be doing this as we go along. So I will be collecting some questions here. I, in fact, already received one question before I even asked you, and I think it will be a very nice one to debate. But maybe if there is an immediate response to the question about the simulations that anyone...
I mean, I can tell you what we are trying to do is to run whole galaxy simulations and then zoom in. So, you know, this is something you can do with AMR, with particles, you know, so you simulate a whole galaxy, then you go back and pick out a patch, you know, and you run the entire galaxy at, say, 1,000 solar mass resolution for, you know, half a gig a year. Then you increase the resolution to 100 solar masses and run for, you know, tens of mega years to let it re-equilibrate, or 100 mega years, and then you pick out and you simulate that at, say, 10 solar mass resolution for 30 million years, and that's the sort of way we've tried to get around this environment problem.
I have the simulation domain. Let's say if I'm just trying to zoom in and one in the patch, I know the gas that's coming into that into that little cell. The gas that's coming into that cell and out of that cell. Now, into that cell, obviously, in my first simulation, that resolution is limited, and I'm now gonna have to create stuff out of it to boost up boost up the resolution. Am I understanding it correctly? I mean, how can I create that if I don't know it from the first simulation? If I don't know it from the resolution, then when I zoom into it, when I increase the solution, in any sense, I'm creating something out of it.
Yes, and it's total crap for the first.
Okay. Okay.
Yeah, no, you're absolutely right. You have to throw away the first n years after you increase the resolution because it's total bullshit.
Right. Okay.
So you have to wait for it to re-equilibrate to do higher resolution.
Okay. Okay.
Awesome.
Yeah, just two brief comment. I mean, how to do it? I mean, we're also trying to do these things. The idea is actually to come back in time. When you identify regions of actions and so on, you actually throw what has been done. You come back in time, and then you read relations allowing for essentially more resolutions or whatever. So in this case, you get more coherence. The second comment, which is different, but I mean related to your question, is it's very important always to ask yourself, what do you want to do? Question you want to ask, because simple setups can, be extremely useful for many questions. And the question is, okay, if I need to go for a more complex and Zoom are immensely more complicated, what kind of questions I may not be able to address with the simplest setup I have been studying. So that's always the questions, why do I do something and what I want to get out of that. It's a fundamental question, I think, when you do science.
Excellent. So even though we already have another question that has been asked, I will prioritize the student questions first. So, and if we have time, we'll go back to the big picture philosophical questions of when is star formation actually solved? And what do we even mean by that?
When we all get tenure.
Yeah, I mean, okay. But yes, so would anyone else like to share their question? Ooh. You get chocolate.
Maybe like a sort of similar thing, but from a more observational perspective. Like what the stuff that I'm doing is like looking at these sort of massive star forming regions, trying to identify the cores, and then say something about maybe the protocluster formation and evolution process, and then maybe more specifically from that, the massive star formation process. But in both sort of the philosophical sense and in a very literal sense, I'm limited by the field of view of the image and can't see what's going on outside that. And so any sort of conclusions I draw from, some ALMA map of a region is limited by the fact that I don't know what's going on outside that and can't really say anything about, how, reading lots recently as well about like this hub filament system idea and how like large, filaments sort of converging on a clump might contribute to accretion in general, but on a larger scale. And so I guess, again, just how are smaller scale things affected by larger scale things, but maybe in the more specific context of massive star formation and cluster formation.
Okay, do I understand correctly that on some level your question is also about how to interpret your results in a sort of broader context?
Yeah, or even, again, like from when you're working with observations, like each sort of instrument and wavelength has such sort of specific, data reduction processes and interpretations, and so hard to just combine observations at different wavelengths and scales to say something about star formation in a less specific sense and more building up this bigger picture idea of how all the scales interact.
I think this is a really good question. I can maybe comment on this anecdotally very quickly. So this has been a big problem in the galactic center for a long time, right, in which we've observed individual clouds. But then we have the much bigger picture of this ecosystem, what's going on, and I'll talk about that tomorrow. But anecdotally, I was working with a colleague of mine who was working on star formation in an infrared dark cloud, and we had fairly high resolution observations. And there was something interesting in the gas kinematics that we were looking at, sort of looked like a converging flow towards this infrared dark cloud. And what we did was to obtain as much ancillary data on different scales as we possibly could. And when we did that, we discovered that this infrared dark cloud was actually sat at the edge of a supernova remnant on one side, kind of a massive H2 region on the other side, and this infrared dark cloud is sat in between. So I think it is a really important point that you've just raised. And I think, so in one of the slides that I had in my talk on filaments the other day, I have this, there are a lot of resources available to you that mean that you don't necessarily have to go and write another proposal to get another scale, and so you can always try and look into that. But I think what you've just said is a really important point.
Does anyone else want to comment on that?
I would just add to that, I agree.
And during my talk, I forgot to highlight your talk because everything that I presented was from archival data. All that Orion stuff, of course Orion's special because everybody looks at it, blah, 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 but anyway, it's a treasure trove, and none of that was proprietary. And he said, you can go to all these websites, blah, blah, download Apogee data, CO maps, N2H+, whatever, Herschel, et cetera, and combine it. So I think it's also about an open-mindedness to actually not only pigeonhole yourself like an observer, I do this wavelength, super boring.
Or even to the point where you're looking at a cloud, right? You know, the context there.
Yeah, I have a thought that might make our lives even more painful and miserable. Which, yeah. The end of the, on the scale diagram you had, the left-hand side ended at 1/10 of a parsec. I think we actually need to think maybe down to 10,000 kilometers or so, because questions about how many stars go supernova, when they go supernova, how much energy they go, even do they go supernova, as well as what is the process that drives stellar winds, what sets the UV luminosity of stars. All of those are internal stellar processes that that depend on things like rotation, metallicity, stellar structure. So even knowing how stars evolve internally, which can be connected to how they're formed, can feed up the ladder potentially all the way up to galactic scales again. Which we're never going to get down to 10,000 kilometer scale simulations of galaxies.
Yeah, just fun stellar revolution, people to figure that stuff out for us.
Yeah. I think that's the thing is we assume we're working on the hard problems. Like stellar, if you talk to Georges Manet, he'd be like, oh yeah, star formation's easy, stuff just falls down, and then it makes this horribly complicated thing that's a star. And we're working on the hard problem, but it's hard problems all the way down. Yeah.
He should get on that.
Okay, on that cheery note, I don't think that we're going to be able to answer this question, but any more student questions?
So I've been working on observations of the cloud-cloud collision, and Rodrigo has been looking at observations of protostars in PV space. And so the question that we came up with together was, do cloud-cloud collisions actually cause star formation, or do they disrupt star formation? Because in my cloud-cloud collision, I don't see any evidence of any high-mass star formation to do with the cloud, and low-mass star formation is a little bit difficult to see resolve.
Excellent question. Would anyone care to try to answer?
Maybe it will depend on the sort of they are not balls, no. But if you treat them as well-defined objects, maybe it will depend on the impact parameter and that kind of thing, such that there will be situations in which cloud-cloud interactions will produce shear, which was mentioned in some talks, and it will probably tend to break apart the clouds more than accelerate star formation. But I guess there will be some circumstances in which cloud-cloud interactions. I actually don't like the word collision for the cloud-cloud interactions will enhance star formation rate, no?
Yeah, so I think I also not super fond of the term collision, but I don't think I fully understand the simulations either, in the sense that one could envision maybe hotter, not yet molecular material in the ISM moving around and, quote, colliding, and then maybe forming a cloud. I'm not sure, right? But just naively, if I look at the galactic, our galaxy, our disk, it's pretty kinematically cold, and everything's rotating in a very orderly fashion, so it's hard to imagine for me things like the ALMA-MF protoclusters or something like this actually colliding with each other, these already formed objects. So to me, I wouldn't mind, I guess one way of putting it is understanding a bit better the scenario.
I mean, the topic comes up, for example, in the context of the galactic center, where you have a bar and then...
Right, but I've seen many papers using cloud collisions to explain things out here, not in the galactic center, right? And so then I get a little bit, I'm like, really? But then if they go to the antenna galaxies, this train wreck, I'm like, okay, I'm down with this story, right? So, you know, I think it's not a scenario that can be generically applied to all things, which is normal. But anyway, it's a bit confused, at least on my side, in my head.
Savannah, are you working on W51? Are you working on W51?
No, I'm working on cloud collision along the bar.
And the bar.
Yeah, I was just going to add to that. So I think the antenna is a really good example, and I also think the galactic center, where we know that things have to collide along the bar to actually lose angular momentum and move inwards to the center of the galaxy. The other thing the final thing that I would add here is that the kind of observational signature of a cloud-cloud collision is pretty ambiguous, right? And it's pretty shaky. So, you know, claiming something to be a cloud-cloud collision is in itself, purely from observations, not an easy thing to do, and therefore it's kind of a difficult question to address because of that, right? It's not an unambiguous signature, and the kind of things that are put forward, in my mind, as evidence for cloud-cloud collisions could be consistent with several other scenarios, right? So, yeah.
Yeah. I mean, okay. Since the concept of cloud is also kind of vague and nebulous, what prevents from one side of the sort of cloud at some point hitting the other side of the cloud? Like, is it a cloud-cloud collision, or is it then the cloud just collapsing on itself? In principle, it could, like, yes, I mean, this is just to add to the fact that the definition is kind of vague. In simulations, we could separate these things. We could really just have two blobs and smack them together. In observations, it's, yeah. Does anyone else want to say anything more about this question? Okay, but, okay. if we are done with this question, yes, then let's go to the next one. Awesome.
Yeah, I thought it would be fun to change the scale a bit. So I mainly use or work on galaxy evolution and formation. And I'm not sure if anyone knows the Van Dockum et al. 2013 plot. But basically, he uses Milky Way progenitors in Hubble and tries to put a star formation rate at a Milky Way at, for example, redshift 2, and makes a very nice parabolic shape from redshift 0 to redshift 3-ish and has a peak at 2. And I really want to know how it now looks with JWST data. I want to know how it looks now. And so this is my quest of someone please making this plot. Please make this JWST plot. I would love to see this going into like redshift 5, maybe redshift 6, and how actually the star formation history of the Milky Way or a Milky Way progenitor or something, just say this galaxy of this size, would look like if we would really probe it back. Please, if someone has this data, please make this plot.
Okay, something like this. We have not really covered such large scales yet, so I don't know, maybe the answer to this question is about to come up, but does anyone want to try to answer this now? Yes?
Would you like a chocolate? I can get you a chocolate.
No, I'm joking. Maybe I didn't understand well the question, but you are asking the cosmic formation is the star formation rate per commoving volume as a function of redshift with JWST.
Yeah, so I mainly really would like to know of kind of like a Milky Way-like galaxy and how its star formation history looks like in observations. So Van Dockum tried to do this with Hubble in 2013, going on to like redshift 2.5, and just kind of cherry-picking Milky Ways at different redshift, like this is a Milky Way, this is the star formation rate plotted.
I mean, you are trying to, yeah, I understand. You are trying to, one realization, which is the Milky Way, what do we see associated with observations of galaxy at a different range. I think it's a tough question, but yeah, not impossible to answer. I haven't seen that plot then.
Okay. Yes, somebody over there.
Also, like, you are tracing back the evolution of our own galaxy, and even that simple concept of, like, which mergers were undergoing, like, which are the peaks, because we are sure that the galaxy, or that's what some simulations say, have been undergoing several mergers during the history of evolution, and those mergers are likely to induce some of these peaks. So it's really hard to catch those things and also space them in time or regressive. But I know there is some people attempting to do so. If I cannot share more things, but if you are happy with that piece of information, there are some people trying to find it out. But it's, as it was said, it's a really tough question. And even though you need to make lots of assumptions, so it's just a snapshot of several assumptions that we do over our galaxy, and then that's what you came. But I think it's a really nice question. I would also add, like, how is Milky Way, a Milky Way-like galaxy at redshift 7, 8, now that we are opening the Pandora's box of galaxies at even redshift 12? I think yesterday in Archive there were some papers on candidates of galaxies at redshift even 13. So that's also a really nice question. Like, can you separate the star formation rate of a galaxy there and clouds at redshift 13? That's also another question that I would like to propose. Like, what's a really massive cloud and a galaxy at redshift 13? Which is the difference? Because I don't actually know the difference.
Okay, I'm going to add it to this. I don't know if these are necessarily the kind of questions that we have answers to yet, right? But they do have great value to be posed, because this is something to be striving towards. So unless these are indeed answered questions and I am just not aware, looking at people who were.
I can tell you what one simulation with one set of star formation and feedback physics predicts for the star formation rate of the Milky Way at redshift 13, but that's just a prediction. Like, nature could be, it could be very wrong, and nature will smack me down in good time eventually. But I think, just thinking about the halo mass of the Milky Way progenitor at redshift 10, probably going to be hard to do observationally. Like, we're starting to get good ideas as to what the progenitors of clusters look like at redshift 10 to 13 or so. But if you've already formed 10 to the 9 solar masses worth of stars by redshift 13, you're not going to sit around twiddling your thumbs for the remaining 14 billion years of the universe's history. You're going to be a cluster by redshift 0.
All right. Excellent. We might have time for one more question if... Excellent. You guys are great at asking questions today. I'm really loving this.
So first of all, I just want to briefly comment on that, to say that I think the best way to go about this question is through gravitational lensing. And there are people working on that, especially from where I'm from. The University of Montreal, they have a group working on getting GMCs in these high redshift galaxies using ALMA data through lensing. But my question is that since we talk about cloud collisions and in the galactic center, my question is that why do we see star formation not so intense in the galactic center, but it's so intense in other barred galaxies with like nuclear rings and stuff? Like, what's the difference?
Really glad you asked that, because I'm going to give an entire lecture on it tomorrow. So I think that's probably a good place to call it.
Excellent. Yes, I've added your question, but yes, stay tuned for Johnny's lecture. Awesome. Yeah, thank you guys so much for participating so actively. Please keep writing questions, because this is the only way that they're going to get answered.
Yeah, and also we'll have another discussion on Friday, right?
Yes, yes. So this was just like the taster for what's to come.
Okay. In which case, should we thank Mark and Maya again for their talks this morning? And coffee break, right? And then back at 12.
Oh no, sorry. Oh God.
No, right there.
Yeah.
Yes, don't kill the students. That's bad, Johnny, bad. Yes.
It's more efficient, like, because some kind of imagine that you have a supply from cosmic which is supposed to be pristine gas.
Yeah.
At some point. So it's more efficient for that gas just to mix with the gas of the galaxy and then I spray that to grab the molecule.
Absolutely.
It's absolutely it's more efficient. So that's the process that you expect for nowadays.
Yes. Yes, absolutely.
But not for solution.
No, for top 3, if there really are metals, you have to do another. And if you're interested in the comparison quantitatively,
Elsewhere in the galaxy,
there's actually, like, there's a problem in my
components with lots of star formation.
that problem set 5 has exactly that calculation. So,
The other thing as well is people actually try to time scales to entire calculation.
Yeah, that's the thing. No, maybe that is the problem also with switching some stars so that you can prove. But if you install it here, I'm already happy, and then that's already fixed. Yeah. Because I don't know, does it work with this? Oh, okay. Then I have it, but it's not issue. No. Yeah. But so in Division, you're gonna do because And also, like, you know, they give you the laptop with the admin and your own name, so you can just do the admin name. Maybe they want to, like, keep you up afterwards and then use the laptop.
Yeah, but it's weird that you cannot install anything, so you
What?
I have to be the chair.
Oh, you're the chair,
Yeah,
okay.
this time is. Okay, so this was the one. Okay.
No, I can see the clock. Yes. Yes, the clock is right there. Yes. Yep.
So now you're gonna, okay, you're going to the next case.
Yes. Yes, this is the hinge where we go to the extra part.
The chocolate is here.
There's more here.
Oh, okay.
There's more. Yes. Yep. It's the most important duty of the chef. Everyone else is with, like, they're just going around and giving people chocolates. No one else is throwing. You're not,
To move my stuff.
if you're not throwing them, you're not.
I have to be careful not to eat stuff on the face.
The danger is part of the experience.
What people go on roller coasters, right?
What was that?
That's why people go on roller coasters.
Yes, exactly.
You have to have just, you might get chocolate, you might get hit in the face with chocolate. It's all part of the fun.
Exactly.
Well, do the slingshot. That would really raise the stakes. It achieves higher velocity stuff than it achieves.
Especially with the bigger candy, the Spanish candy.
Yes. Yeah.
Where is the free space? Here?
Oh, we're looking for the, it's right there. Yeah. Is that about the right volume? Was that good? Okay. So we'll talk about the observations, then we will develop some general principles for sort of theoretical understanding about radial inversions in galactic disks, and then we'll talk about sort of two classes of models people make to try and understand what's going on. So let's start with the observations. When I started with observations previously, I had, someone looking backwards into a telescope. We're now at the final lecture, so I'm rewarding you with cute Australian baby animals. This is a wombat. And yeah, that's a baby wombat. They are very cute. They eat grass and everything else. What? Yes, the pouch backwards. Yes, the pouch opens backwards because, and the reason is because they're burrowers, and so that way dirt doesn't get into it. The other two facts I will tell you about wombats while we're here are that their poop is cubical. True, they poop in cubes. Yeah, mysteries of nature. All right, that's one. And two is they're burrowers. Their defense strategy is if they get attacked by a predator, they dive into one of their burrows, and they then plug the hole with their armored ass. So wombats have an armored ass, which they use to like plug the hole behind them if they're being attacked by a predator. So, to the cubical poop, it could be. So these are your two wombat facts. All right, let's talk about, if I can get it to stop skipping, star formation laws. All right, so the most basic form of this is what's called the Kennicutt-Schmidt relation. And this was established by Rob Kennicutt in 1998, but really the conjecture goes back to Schmidt in 1959. All right, and Schmidt's conjecture was that if you have some blob of gas with some density, the rate at which it forms stars will be a power law in the density, which, it's astronomy, everything's a fucking power law. Nonetheless, that was his conjecture, and Rob Kennicutt found a way to test it. All right, so here's a more recent data set. On the x-axis is the total gas surface density of galaxies. So here we're looking at whole galaxies. So the way these data are taken is you take an entire galaxy, you measure the total amount of gas, you define some effective radius based on, the half-light or something like that. So you take mass, you divide by the area within that radius, you get a gas surface density. You include H1 and H2 together, and then you measure the star formation rate inside that same radius, and you plot surface density of gas against surface density of star formation. And you get this relatively tight correlation. The slope of this is about 1.4. And it's just worth noting, this is like, if you look, this is one of the 20 most highly cited papers of all time in astronomy. If you look it up on ADS, it has like 5,000 citations or something like that. So you get this tight correlation. Now, the slope of this correlation, I said it's 1.4, but now I, come to one of the dirty secrets that's swept under the rug, which is that the slope really depends on this thing alpha CO. What is this thing alpha CO? I could give an entire lecture about it. It's horrible. But it's basically that the observable that we actually get to measure is the CO surface brightness. Turning that into mass is not entirely straightforward, and there are different models and theories for how you do that. And depending on exactly what you assume, you can make the slope here as shallow as about 1.1 or as high as about 1.7. All right, so depending on what you assume about alpha CO. So I say it's 1.4. In reality, it could be a little shallower or a little steeper than that. We don't really know. All right, so that's one version of this correlation, just whole galaxy averages. But you can make other correlations too. If we're sticking with the whole galaxy scale, you could say, well, all right, what if I bring in not the gas surface density, but period? That's what this T dynamical is. It's just the orbital period of the galaxy. And instead of plotting gas surface density on the x-axis, I instead plot surface density divided by dynamical time. And I get a correlation that's about as tight as the original one, but now has a slope of 1. All right, now one way of reading this, if you read this off, all right, the units unfortunately got cut off here, but one way of reading this is that a galaxy turns 10% of its gas into stars per orbit. All right, that's the basic meaning of this. Every time the gas goes around once, 10% of it turns into stars. All right, so great, we've got this correlation. Incidentally, this leads to what's called the star formation fueling problem, which is that the Milky Way is 50 orbits old. And if you use up the gas in 10 orbits, why haven't we run out? That's a separate question, which we're not going to get to in this lecture, but it's just something to keep in mind for future ones, and maybe some of the future lecturers will talk about it. All right, so that's local galaxies. In the past 10-ish years, it's become possible to put more distant galaxies on this plot. All right, so you can say, well, all right, what if we don't just limit ourselves to local galaxies? What if we high redshift galaxies? And if you do that, so here's the two forms of the Kennicutt-Schmidt relation. Here's the total gas surface density one. Here's the one with dynamical time. All right, what you find is that if you put like high redshift galaxies, like what's labeled SMGs here, these are submillimeter galaxies. These are galaxies at redshift 2 or so that are selected based on being very, very bright in the submillimeter, but not in the optical. And the interpretation is they're so dusty that you're basically not getting any starlight out of them. All of the starlight's getting absorbed by the dust. So they're super bright, but all of the light comes out in the infrared or in the millimeter. Then you see that there's a sort of displacement between them and the sort of normal star-forming galaxies in this diagram, but they sort of come back together if you go to this diagram. All right, so maybe that says, all right, this is the fundamental one, this one's sort of an accident, but again, this depends on exactly what you assume about alpha CO. And this is for a particular choice of alpha CO, and for different ones, you can make these two sequences come closer together and these two move apart. All right, so nonetheless, we have the sort of rough result that high redshift galaxies and local galaxies look fairly similar in terms of their Kennicutt-Schmidt relation. They live on the same relation. They don't live on the same place in that relation. On average, high redshift galaxies have higher gas surface densities than low redshift galaxies. So they slide to the right on this relation. Galaxies are more gas-rich at high redshift, but they're moving along a single relation. And you can find local galaxies that are just as gas-rich as high redshift galaxies, and when you do, they live in the same place on the relation as those high redshift galaxies. All right, so that's high redshift galaxies. Another class of galaxies you can look at and try and put on this relation are dwarfs and low surface brightness galaxies. All right, these are local galaxies, and when you do that, you find that dwarfs and low surface brightness galaxies seem to sort of fall off the bottom of the relation. So these black crosses are the sort of normal spiral galaxies. And then these colored points from this paper by Wider et al. Are local dwarf galaxies measured with GALAX. And you'll notice they sort of fall below the relation. It looks like the relation is sort of turning down here. All right, so that seems to indicate that maybe something a little bit different is going on in these galaxies. Now, caveat, there are major data issues here. If we're looking at these galaxies, these are all local dwarfs. They're metal poor. And in metal poor galaxies, CO is very, very dim and hard to observe. And the conversion between CO and molecular gas is even more uncertain than it is for spiral-like galaxies. So in these galaxies, it is basically assumed that there is no CO, or that there is no H2, that the gas surface density is dominated by H1. All right, so if you look at, now, if you added some more gas, if you said, suppose H2, that would actually make the discrepancy even worse because these points would move to the right. Nonetheless, you have to keep in mind that there's a big uncertainty here. I should also note that it was only possible to do this with UV. So we talked about star formation tracers in a previous lecture. What made it possible to put these data on this plot in 2009, when they were not on Kennicutt's original plot in 1998, is the launch of GALAX. Because these galaxies are very, very dim in H alpha, they have low star formation rates, And it's just very, very hard to see the H alpha from the ground because of sky brightness issues. So it's hard to subtract off the sky and measure low surface brightness H alpha emission. Whereas from space, you could do this with GALAX, and you could very easily see these galaxies. Right? And this is, now, note that this applies to nearby spirals. Based on integrated, the depletion time has to be lower in starburst and high redshift systems. All right, and the way you know that is simply that if I go back to this plot where I'm using the integrated galaxy relation, all right, this line is steeper than these dashed lines are lines of slope unity. Here. So the statement that all galaxies have depletion times of sort of 1 to 4 gigayears, pixel by pixel, is true of things that live down here. Clearly can't be true of things that live up there. All right. And although I'm not showing it on this plot, you get a similar result in Now, a basic thing you can do with these data is try and say, well, all right, you know, we talked about this epsilon FF before as a fundamental parameter. What epsilon FF does this correspond to? So how do you get that? Well, there are a couple of ways, but the most basic one is you take each of these pixels, and you've got the gas surface density and the star formation surface density. So the last thing you need for epsilon FF is the free fall time. Well, how do you get the free fall time? A couple of ways. One is you can assume the disk is in vertical hydrostatic equilibrium, and from the velocity dispersion and the stellar surface density and the gas surface density, you can work out what the gas scale height has to be. And if you know the gas scale height, you know the surface density, you know the density. There are other ways you could assume a scale height. There are a variety of ways you could try and do this. But that gives you the volume density, which is the thing you need to get the free fall time. And then you can say, well, what epsilon FF does this correspond to? And the answer is 1%, like everything else. So you can try and put all of these galaxies on this diagram where now the x-axis is H2 surface density divided by freefall time, and the y-axis is star formation rate. And the blue points and the green points here are resolved pixels within nearby galaxies. Efficient at forming stars that of the Milky Way, and you cram it into the central 500 parsecs of the galaxy. That's basically what ARP-220 is. And so the density is super high. The mean density of the ISM in ARP-220 is 10 to the 4, 10 to the 5 particles per cubic centimeter. ARP-220 is and so it forms stars like crazy, but that's because its freefall time is really short. Okay, so thus far we've been talking mostly about atomic gas, or about molecular gas. Right, so what if instead of on the x-axis we put, instead of putting H2, or total, we put H1? And if you put H1, all of a sudden things look very, very different, right? There's almost no correlation here between the amount of H1 and the star formation rate. Instead, what you see is this just sort of vertical wall, right? In the inner parts of galaxies, the H1 is basically just always about 10 solar masses per square parsec. And the amount of star formation is totally uncorrelated with that. Now, hopefully, why you see this wall at 10 solar masses per square parsec is clear to you, having hopefully paid attention to my last lecture. Someone want to venture an answer? Prove to me that you haven't forgotten everything in 2 hours? Yes.
Isn't that the surface density where H1 gas will turn into H2?
Exactly. That's exactly what's going on here. Give the woman a chocolate. Yeah, I mean, the reason this wall is here is simply that, like, there are plenty of places in galaxies where the surface density is, 30, 40 solar masses per square parsec. It's just that only 10 of that is H1. After that, any additional gas you add turns into H2. All right, and that's also sort of why there's presumably no correlation between star formation and H1. It's that, you're looking at, like, the 10 solar masses per square parsec of material sitting on top of the 50 solar masses per square parsec of H2, why would you expect the depth of that shielding layer to correlate with anything? All right, now, that's true in inner galaxies. Something interesting happens if you go to outer galaxies. All right, so this is spirals, but outside of our... So this is, again, H1 versus star formation rate. And here there actually is something of a correlation. Now, you'll notice this is at surface densities way below 10 solar masses per square parsec. And this correlation is there, but the depletion times are huge. All right, I'm not sure if from the back of the room you can read off the labels on these dashed lines of constant depletion time, but these numbers are depletion times in years. That's 10 to the 8, that's 10 to the 9, that's a gig a year. So normal galaxies, their inner parts live along this line, depletion. your metallicity. In the SMC, which is lower metallicity, that transition occurs at a higher surface. In the LMC, which is closer to Milky Way in metallicity, it's half solar, it occurs closer to the 10 solar masses per square parsec we see in the Milky Way, or similar metal-rich galaxies. So this is the observational phenomenology. Something further you can do is you can say, well, all right, this is looking at just density, but maybe the stars matter too, right? After all, they add gravity. And so a common way of the dynamical equilibrium pressure. All right, so by the dynamical equilibrium pressure, what I simply mean is the pressure that is required to hold you up against the combined self-gravity of the gas and gravity of the stars. All right, so you can work out in a plane parallel geometry, if I have a certain stellar profile and I have a certain amount of gas, what does the pressure have to be in the midplane to be in equilibrium? That's the pressure I mean here. And so you can look at the molecular fraction and the star formation rate versus this pressure, and you see that there's a pretty good correlation, as good as the one with gas surface density. Now, is this more fundamental, or is the metallicity more fundamental? There's a degeneracy here in that, regions of high metallicity also tend to be, they're bigger galaxies. Regions of low metallicity tend to be regions of low pressure. So it's unclear whether metallicity or pressure is the more important variable. All right, so this is all on kiloparsec scales. If we continue with the observational phenomenology, I can zoom in even more. All right, and here, this is CO versus, so blue here is CO, orange is H alpha. All right, and this is Catherine Kreckel's work again. And you see this decorrelation between the CO and the H alpha. And this is exactly the phenomenon we talked about before of the CO and H alpha decorrelating on small scales. And the interpretation is that this is evidence of rapid cloud destruction. All right, so I want to talk about one more observational thing, and then we'll start to talk about the models a little. So the final sort of observation that you have on large scales is you could say, well, what if I don't use CO? Right, CO is the easiest thing to use if you want to measure the gas in galaxies on large scales, because it's the brightest molecular line. But it's not the only one. You can also use HCN. All right, now why is that interesting? Well, the reason is critical density. All right, the critical density of CO, once you include radiative trapping effects, is about 100 per cubic centimeter. So CO is basically tracing most of the molecular gas. HCN, on the other hand, all right, remember that the critical density depends on the collisional excitation rate coefficient and the Einstein coefficient. HCN has a much higher Einstein coefficient than CO. As a result, it has a much higher critical density. It's more like 10 to the 4 per cubic centimeter. All right, so if you look at HCN, you're tracing denser gas. Now, this is hard observationally because it's not as bright, right? HCN on average is 10 times dimmer than CO in a typical spiral galaxy. So if you want to map it at the same signal-to-noise ratio, you need to observe 100 times as long. Right, so this is something that was just not doable on large scales in the pre-ALMA era. But with ALMA, you can do it. All right, so what do you see in HCN? All right, well, you can look at just, say, total HCN luminosity versus, say, IR luminosity. It's a proxy for star formation rate. And again, you have a very good correlation, nearly linear. Now, one thing you can note immediately is the slope of this is 1. It's not 1.4, it's 1. All right, so that's interesting. All right, and there's a scatter. This is just the same data, but here's the HCN, and here's IR divided by HCN. You see that there's this, sort of good correlation. All right, so how can we interpret this? Well, all right, one simple interpretation you can give is, well, all right, since there's a near linear correlation between HCN, which is like the mass of dense gas, and IR, which is like the star formation rate, maybe there's a universal star formation law that says that there's a certain star formation rate per unit mass of dense gas. And observers like this because it's really simple. right? It's really, really simple, and observers are simple-minded. That was just to wake everyone up. That was, you know, if you're falling asleep, I insulted you. There are a lot of people who like this. That's the 0th order answer, but it's not right to more than 0th order. First order, in fact, the IR to HCN ratio is lower in higher pressure galaxies, so something more complicated is going on. All right, so a suggested explanation for this is that the 0th order answer, it's near linear, is because, well, the star formation rate is this universal 1% epsilon FF times mass divided by free fall time. Well, and any galaxy where you look at HCN, you're looking at gas of about the same density because the density that HCN picks out is determined by quantum mechanics, right? HCN is tracing gas at a density close to 10 to the 4 because quantum mechanics says so. Doesn't matter what galaxy you're looking at, it's always about 10 to the 4. That's the first order answer. All right, but that's not exactly true. And if I go to a galaxy where the mean density is 10 to the 5 per cubic centimeter, well, then HCN is tracing gas at a density of 10 to the 5. So the slight deviation from linearity is caused by this not quite being true. All right, but you could, leaving that complexity aside, you could just say, well, all right, I have a certain IR to HCN ratio, right, in whatever insane observer units this is. And it is like insane observer units, right? It's like Kelvin kilometer per second per parsec squared. No. Yeah, okay, I see people in the back. I mean, at least it's not fucking magnitudes, right? Like, it's better than magnitudes. This is actually like, you know, like, it. Yes, it's solar luminosity per Kelvin kilometer per second per square parsec. Whoever invented that unit should be flogged. All right. But whoever invented magnitude should be, you know, tarred and feathered. Except that, you know, they're an ancient Greek dude who's been dead for 2,000 years. So really, what's the point? All right, so in insane observer units, you know, this is the ratio. All right, but you can go and then, you know, you can do what a theorist does and say, all right, in order to reproduce this observation in insane observer unit. All right, so here is HCN luminosity. Now, this is a sample of Milky Way clouds. And I'm going to focus in on some little patch of it at some distance r0 from the center. And in this patch, there's some local rotation speed v. And I'm going to set up a Cartesian coordinate system in my little square patch. X is the direction away from the galactic center. Y is the direction aligned with rotation. And I'm going to say I've got an isothermal gas in this patch, which has some sound speed cs. And I'm going to ask, what happens if I perturb it? So what I can do is I can write down the equations of mass and momentum conservation for this little patch in the Poisson equation for self-gravity. All right, and then what I do is I say, let me take a background state that's uniform, and then let me perturb it. And I'll perturb it with a radial perturbation, which varies with position and amplitude as a Fourier mode. All right, why do I do this? Well, there are two basic reasons. One is that I can write anything as a sum of Fourier modes, right? So I'm allowed to consider a general perturbation as just a sum of Fourier modes. And the other is that the purpose in life of Fourier modes is to turn partial differential equations, which are horrible, into algebraic equations, which are less horrible, right? Because when I take, d dx of this, I just get this times I k. When I take d dt of this, I just get this times minus I omega. And so my PDEs turn into algebraic equations, which are much easier. All right, so I take these small perturbations, I plug them into these equations, I do a lot of math, I drop all the terms that are higher order, and the basic outcome of this is what's called a dispersion relation. Dispersion relation is, what you find is that you can satisfy these equations not for arbitrary k and omega. The spatial frequency k and the temporal frequency omega have to obey a certain relationship with each other, which is called the dispersion relation. Here's the relationship they have to obey. All right, here, Cs is the sound speed, sigma naught is the unperturbed gas surface density, omega is the rotation curve. All right, and you have to obey this equation. The right-hand side is a quadratic in k, all right, which has a minimum at some particular value, right? It's just parabola has a minimum. All right, so you can ask, at this minimum, is omega positive or negative? Right, well, so here's what the minimum is when you just plug in. It finds this kappa is the epicyclic frequency. And then you can ask, well, is this number on the right-hand side for omega squared a positive or a negative number? All right, now, if it's a positive number, we're all good, right? Omega squared is a positive number. You take the square root of a positive number, you get plus or minus some real number. All right, you go back and you look at your solution, you get e to the I plus or minus omega t, and you just get something that oscillates like a sine wave. Fine. If omega squared is a negative number, that's okay. Right, because omega squared is a negative number, you take the square root of the negative number, you get an imaginary number. You plug an imaginary number into here, the I cancels, and you have one solution that looks like e to minus a real number. That one's fine, that solution decays. And one solution that looks like e to plus a real number, and that grows exponentially. And so you start with an infinitesimally small perturbation, and it grows exponentially in time, and that's what we call an instability. All right, so you can immediately write down the condition for instability, and this is the famous Toomre Q. This is Toomre's Q, and the interpretation is that if there's a lot of shear, kappa is big, or there's a high sound speed, a lot of pressure, Cs is big, this numerator is big, and the disk is stable, these things stabilize it against gravity. If there's a lot of gravity, sigma naught is big, and this quantity on the right-hand side is smaller than 1, the disk is unstable. All right, and it'll fragment. Incidentally, one very useful way of writing down this condition is that Q equals 1. The stability line corresponds to when the free fall time is about the same as the orbital time. That's just a useful thing to keep in mind. All right, so if you take a disk where Q is less than 1 and you simulate it, you get something that looks like this. Right, so this is a simulation that started out with a laminar disk, but Q was less than 1, and this is what happens to it. All right, so one of our sort of boundary conditions we might expect in a theory of star formation is that Q should stay near 1, right, or shouldn't go much below 1. right? It's bad if this happens to your disk. All right, so one of the ingredients you might want is that disks maintain Q of about 1. All right, so now let's talk about the vertical direction. And here's my out of order slide. All right, so if you look at the Milky Way, the scale height is like 150 parsecs, and similar for other nearby disks. And this sets the density at the midplane, and this is plausibly related to the star formation. And that scale height is determined by the balance between gravity and pressure. All right, so what can we say about the vertical structure of the ISM? All right, and again, I'm not going to do all the math. I'm just going to, sort of walk you through it quickly. So walking you through it quickly, we start with our momentum equation, and we've written it in like a tensorial form here because it makes life easy. So we've got ddt, the rate of change of the momentum. We've got pressure plus advection in this term. We've got the Lorentz force here, and then we've got gravity. And we're going to set up a coordinate system with a disk centered at z equals 0. And we're going to take the z component of this equation, which is this. This is just taking, this is an equation, this is 3 equations, because v is a vector. I'm just taking the z component of that equation, and I get this equation. And then what I do is I say, I'm going to consider some area A of the disk bounded by some curve S lying at constant z. And I'm going to just average over this area. So I calculate this average, and I get this equation. All right, I can separate the x and y components. This is algebra, whatever. All right, I apply the divergence theorem, algebra. All right, and I wind up with this equation. So now we actually get to do some physics, not algebra. What does this equation say? This says that the time rate of change of the vertical momentum averaged over this slice of the disk. Well, all right, we have the gradient of the vertical velocity dispersion. All right, this is like a pressure. This is like the turbulent pressure. We have the actual gas pressure. This is the thermal pressure. This is the magnetic pressure. All right, this is another term that looks sort of like magnetic pressure. It's actually magnetic tension. We have gravity, and then we have these terms. And in the interest of time, I'm going to skip the exercise, which is to come up with reasons why in steady state these vanish to 0. All right, we'll just skip to the answer. So here's our equation of vertical momentum balance. It simply says that the gradient in gas pressure plus turbulent pressure plus magnetic pressure minus confinement by magnetic tension and gravity equals to 0. All right, so this is the basic ingredient of vertical force balance that we can use in our models. All right, so we've got the sort of 2 ingredients. One is that this gradient should vanish. The other is that Q should be about 1. Now we know the models. All right, again, okay, you cute baby animal here. This is an echidna. For those who've never heard of or seen an echidna, imagine an anteater fucked a porcupine. That's an echidna. All right? That's all it is. All right? Like spiny and it eats ants. Australia is the second Monte Carlo realization of evolution. That's what it is. All right, so let's try and put some of our ingredients together and see if we can make a model. All right, so the simplest thing you could do is say, all right, suppose I do some hydrodynamics and gravity. No cooling, no feedback. I just take an isothermal gas disk. And I simulate it, and I look at, as a function of, say, tumor IQ, what the star formation time scale is. All right, this is a paper from Lee in 2005 where they did this, and you get this nice correlation. And you get the star formation rate is correlated with the tumor IQ. And if you make your tumor IQ high enough, you can get a low star formation. All right, if you observationally, galaxies live at this star formation time scale of about 2 gig years. They live over here. And so maybe if your tumor IQ is about bigger than 1, you can get a long star formation rate. The problem is this is a totally artificial result. This only works because you didn't let the gas cool. Because if you let the gas cool, the sound speed would go down, and 2 raised q would not stay at 1, it'd go down to something very small. All right, so this suggests, a useful approach. You need something to keep q high, but you need something to stop the gas from cooling. And in this simulation, it's just imposed by fiat. Well, how do you keep the gas from cooling? How do you keep the turbulence going? You add feedback. All right, so here's a simulation that includes feedback. You've probably seen a bunch like this. This is one that was done by a student of mine. And you see the disk sort of maintains a quasi-statistically steady state. And that's because supernovae are going off, and that's the dominant feedback mechanism. And if you do this, you get a galaxy that looks sort of reasonably Milky Way-like. So we get this in a simulation. Can we make like a model out of this? All right, so simulations are great. They look really cool, but we're physicists, not Disney animators. Our goal is to actually understand what's going on and not just make pretty movies. Sometimes we forget that. So let's see if we can abstract from that, pretty movie and actually have, a physical model for what's going on. So here's our physical model. All right, so we start with this vertical force balance that we derived earlier. All right, we said that the gradient in the total pressure, thermal plus ram pressure plus magnetic, minus confinement by magnetic tension minus confinement by gravity has to add up to 0. All right, the magnetic tension term is probably small. And then here's our hypothesis. And I should say, I think Eva Stryker is the person most responsible for formulating things this way. All right, we say, well, all right, let's assume that this pressure term is somehow set by the balance between star formation feedback and dissipation. All right, so the basic idea is that, all right, the dominant thing here is probably this, the sort of ram pressure. That represents turbulent motion. In equilibrium, the amount of turbulent motion is dictated by the rate at which I blow up stars, and then that has to be balanced against the rate at which the turbulent motions will damp out if I stop blowing up stars. All right, so let's try and figure out sort of what that term should be. Well, the dissipation rate is fairly easy. You say that the dissipation rate per unit volume is like the energy per unit volume divided by the crossing time. And you get that this E dot is the energy divided by the scale height over the velocity dispersion. And then you say, well, all right, that's the rate at which energy leaves. What's the rate at which it enters? All right, well, that should be like something like the star formation rate per unit volume times the sort of characteristic velocity scale times the momentum per unit star formation that I get from supernovae. So I'm setting off bombs in my galactic disk. Each bomb accelerates a piece of the ISM to some characteristic velocity. So I have a momentum per unit star formation. So I have, how much oomph do I get out of each bomb I set off? That's this P over M star term. Here's my star formation rate per unit volume. Here's my velocity dispersion. And so in steady state, I balance this against this. You'll note the H over sigma cancels. And what I get is that this term should scale something like the energy in equilibrium, which is like star formation rate times this momentum scale. Or you can take models of like supernovae going off and ask how much momentum do I get out of a supernova. It's about 3,000 solar masses, kilometers, about 3,000 kilometers per second per solar mass for isolated supernovae, per solar mass of stars formed. All right, and so I plug that in for this term. And lo and behold, I get the following. I get that sigma dot star looks like the inverse of this momentum scale times g sigma squared. Now, quantitatively, this isn't the right ballpark, right? This is a known quantity. So I can plug in, 100 solar masses per square parsec, typical thing I observe. And I get a star formation rate that's in the right neighborhood. So this is pretty good, but it doesn't completely solve the problem. First of all, we haven't enforced Q equals 1. You can hypothesize extra requirements to set that. But there are some problems. One is that your Tanaka-Schmidt relation is too steep, right? The exponent you predict here is 2. The observations say it's more like 1.4. Can't make it 2. enforcing the requirement that Q equals 1 requires that your free fall time scale like your orbital period, 1 over omega. But with some algebra, this in turn, you can show, implies that epsilon ff has to not be constant, has to be linearly proportional to the velocity dispersion in your galaxy, which is completely contrary to what we observed. We don't see that epsilon ff is varying. All right, and in general, this explains everything going on at galactic scales, but it doesn't tell you why epsilon ff is 1% cloud by cloud, which we saw observationally is the case. So it leaves that as, it's not inconsistent with that, but it doesn't explain why that should be. It also has no explanation for why H2 matters, right? All of this argument had nothing to do with the chemical state of the gas. We saw that there's this strong dependence on H1 versus H2. Where does that come from? All right, so this is one approach, and it does a lot of stuff right, but it doesn't answer these problems. I mean, an alternative approach is to start with the stuff that, I'd say start closer to the observations and work from there. So what you do is you try and figure out where in a galaxy you'll have molecular gas, or gas that's capable of forming these stars. And then you try and say, well, all right, I'm going to try and figure out what epsilon ff is, GMC by GMC, and then just add them up to get the galactic scale star formation law. So let's start with the problem of, why do stars form only in H2? Right? Empirically, this is the case. H1 does not form stars. There's no correlation between H1 and star formation. There is a correlation between H2 and star formation. Why on earth is that the case? All right, and the basic answer, I think, is arrived at in a few papers, one of them by Glover and Clark. And it's the following. Gas doesn't need to be molecular to form stars, but it does need to be cold, right? This is something Patrick said in his lecture. A key thing that makes gas able to compress and form stars is that it is able to cool, to get cold efficiently. Now, where does gas get cold, right? Molecular clouds have temperatures of 10 or 20 Kelvin. The atomic ISM is much warmer than that. Why are molecular clouds so cold? Well, the basic reason is FUV radiation. All right, so we said that, FUV radiation, photons above 11 eV, are the things that destroy H2 molecules. You only get H2 molecules in places where those photons have been blocked out. But those same photons are also the main source of heating in the ISM. Right, 11 eV photons dominate destruction of H2. They also dominate the heating of the interstellar medium. And so there's a very, very good correlation between where gas is molecular and where it's able to get cold. Simply because if you have FUV photons, it will be neither molecular nor cold. If you don't have FUV photons, it will be both molecular and cold. All right, and this affects star formation. So let me walk you through this plot. This is a series of simulations by Glover and Clark, where they're turning on and off various aspects of astrochemistry. So all of these simulations begin with identical initial conditions. They're identical in every way, except that they turn on and off pieces of physics. And then they look at what is just the distribution of the gas in density and temperature that's achieved in the simulation. And you'll notice, so this bottom panel is the full physics simulation, formation of H2 and CO, molecular everything. And you note that there's this tail of gas going off to very high density. That's the stuff that forms stars. Right, so this simulation forms stars. Now, like I said, suppose that we, turn off molecular cooling. This tail's still there. Suppose that we turn off CO formation. Tail's still there. Suppose that we turn off all molecular chemistry. The tail's still there. But what if we turn off shielding? That is, what if we don't let FUV be shielded, we just let it permeate our volume? Lo and behold, the tail is gone. No star formation occurs. All right, so this might explain why it is that you only form stars in molecular gas, and we already understand where molecular gas will form. Great, that's half the answer. Then we have the problem of why the star formation rate in GMCs is so small. All right, now, Patrick already addressed part of this, so I think I'm going to skip through it rather lightly. But the basic argument that you can make is that it's sort of related to turbulence. And here's how I like to think about it. So consider a turbulent medium which has our standard line with size relation. Velocity dispersion goes as size scale to the 1/2 power. All right, we saw that GMCs obey that. It's what you expect from virial lengths. So then you say, well, all right, the maximum mass that can be held up by thermal pressure is of order density times the Jeans length cubed. And you can say, what's the potential energy of a blob of gas of this size? And work out what the answer is. And then you can say, well, all right, what's the kinetic energy of this blob of gas? It's like m times sigma squared. And if you write down how does the kinetic energy compare to the potential energy, turns out that the ratio is just the ratio of the Jeans length to what's called the sonic length. The sonic length is the length scale at which the turbulent velocity dispersion is equal to the sound speed. All right, so here's the key insight. In a typical GMC at its mean density, the Jeans length is way bigger than the sonic length. All right, and so most of the gas is unbound. Even if the cloud as a whole is bound, if you pick a random region within a GMC that's not like centered on some density peak, just pick a random volume, 99% chance it's unbound. It's got way more kinetic than potential energy. And so it can't collapse and form stars. The only places that can collapse and form stars are places that are much denser than the average. All right, so that the Jeans length becomes as small as the sonic length. So you can be quantitative about this. All right, you can say the Jeans length, the mean density is this, and so you need to be overdense by a certain factor, which I've written down here, and then you can ask, all right, I'm just going to skip through this, how much of the mass is overdense by that factor? The answer turns out to be about 1%. All right, so that's part of the answer. Can't be all of it. All right. Bottom-up models do not address vertical force balance or tumor IQ. You have to then put those in as an add. And turbulence will only keep epsilon FF long or low as long as you don't accumulate a lot of mass at high density, which avoiding that requires feedback. All right, but these are sort of two philosophical approaches to trying to explain the Kennico-Schmidt relation. And I believe I have reached the end of my time. So I will take any questions.
Yeah, actually, it's about the cooling molecular versus atomic. My impression is that Simon and Paul have this this sort of viewpoint that the molecular cooling is not so important. I mean, they
absolutely,
yeah. And actually, about H2, there is a kind of chicken and eggs problem. Is that in a sense, is their point of view is because you form dense gas that you form H2.
Okay.
That's I think the point of view they defend, at least in this paper, 2012. So yeah, I mean, I think it's complementary from
yeah, I mean, yeah, certainly it is true. The molecular cooling is not important. What's important is the shield, right? It's blocking the FEV. So I mean, I guess my point of view would be to form dense gas, the gas has to be able to get cold, right?
Yeah, sure.
Yeah, so yes, you know, molecules do not cause the gas to become cold. They don't cause star formation.
Right.
They are simply good, you know, molecules are simply a good tracer of where the gas is dense enough that it can form stars. But to get dense enough, it has to be shielded. Right? It won't, until you accumulate that sort of critical column of 10 solar masses per square parsec, it can't get cold enough to form stars.
Okay.
Just a very quick question about the tumor stability. So I saw this kind of work with stellar disks, and in order to, well, it completely transformed mathematics, and in order to explain cavities and all this kind of, you know, for protoplanetary information. So what's the big difference? Why don't we see these kind of structures, these cavities in galaxies and all this kind of stuff? Because it's completely different results. So
yeah,
what's our explanation?
Yeah, so I mean, that's a good question. I mean, so I'd say that there are two major differences between galactic disks and protoplanetary disk when it comes to tumor IQ. All right, but probably the biggest one is the thermodynamics, right? So if you become unstable in a protoplanetary disk and you start to fragment, what's the outcome of that? Well, it's a giant planet. And the reason is because the characteristic mass at which you become self-supporting is big compared to the mass of the disk, right? The disk, a protoplanetary disk has a mass of, hundredths of a solar mass, tenth of a solar mass at most, right? And the characteristic mass of thing you'd form with that fragment is like a Jupiter, which is a single object that's maybe 10% or 1% the mass of the disk. And that's because you're already pretty optically thick. It's hard to fragment further. Galactic disks, on the other hand, are very, very transparent, right? The characteristic mass of the thing you form if you start collapsing in a galactic disk isn't 1% of the mass of the disk. It's, it's one solar mass over 10, it's 10 to the minus 9 or 10 to the minus 10 of the mass of the disk. So the consequences of becoming unstable and fragmenting are wildly different in a protoplanetary disk than in a galactic disk. I'd say that's the key physics difference.
And the last question is that you showed all these tension magnetic parameter as well, and all this. I suppose these terms keep changing while the cloud or the region evolves, no? So how do you work on this?
Yeah, well, I mean, these are, I have specifically averaged over, right, these angle brackets are, I have averaged over space and time. Right, so I've explicitly averaged the equations over space and time.
So this confuses me because they keep changing because you have ionization, different ionization events. You have the evolution of magnetic cloud of clouds. So I don't understand why, for example, when you start having star formation, I would imagine the magnetic tension would increase a lot.
This is averaged over like kiloparsec scales.
Okay.
Yeah, this is not intended to apply to like an individual cloud. This is like a kiloparsec scale.
Is it possible to do this to smaller scales?
I mean,
the computing.
I mean, you can write down these equations. I mean, you can average over whatever scale you want. But some of the simplifying assumptions I made here would not apply on smaller scales.
Let me just make a comment about the tumor IQ because I had a question as well. Because in your model you have the radial equilibrium and the vertical equilibrium, which are kind of separate in the way.
Yes.
But in reality, in this case, you have a tumor IQ, which would be more like a turbulent tumor IQ, right? Because you not have just the thermal part, but you have.
Absolutely.
So this is kind of a way to couple the two equilibria. I don't know if you have any comment on that.
I mean, yeah, there's a single velocity dispersion that appears in both, and so yes, they're coupled through that.
Right. Yeah. And then the other thing is that you also have the component of the stars that has an effect on Q. In a galaxy.
I was vastly oversimplifying and leaving that out, but yes, that's another thing that's different between a galactic disk and a protoplanetary disk is that you have this component that can't cool.
Yeah.
Right, that you have the stars which are contributing to the stability or instability, but which are effectively dissipationless.
Maybe it's time for Angela to come here.
Okay.
Thanks again.
You're less like you can.
How big it is, like how big is this? Okay. It's not dangerous.
You left out the weirdest thing about it. It's a mammal that lays eggs.
Yeah.
And that doesn't even move the needle for you anymore living in Australia? Mammals that lay eggs?
Yeah, there's a lot of this.
Can you hear me?
Do you need the?
I don't mind. Okay, so. Does it work without the?
Yeah, just plug that.
Haven't come up. Yes,
it is up. So, hi everyone. Since this is my first lecture, I think it's also good I introduce myself. I'm Angela Damo. I'm Associate Professor at Stockholm University, and this is going to be really a lecture. It's a bit weird for me because I teach a lot and not necessarily about the topic I'm most passionate about. So I may be saying things which for me are obvious, which I have ingested, of course, but they are not obvious to you. So maybe take the chance during this hour to interrupt and ask questions, because not everything has to be obvious or learned immediately, okay? So this is your time, actually, for learning. As you see, this is also interesting. I have two double slides. One is with Discover. I like Discover more. Okay, so I highlight in green two words and observations. So this, what we are going to be discussing during this hour is mainly based on observation. We will discuss some theory behind, but it's not going to be a theoretical talk. And we are going to focus on star cluster population in the local universe. So, and I was wondering, when you look at this image, what do you see? ISM, raise your hand, ISM. I see star cluster, embedded star cluster. This is how bad I am. Okay, so I draw here what I see as galaxies in the local universe. We have a main sequence, is where star formation rate correlates with the mass. Is not this a physical correlation, it's simply all the physics happening in galaxies forming stars will eventually build the mass of the galaxies, okay? Then in this type of plot, we will see starburst galaxy being offsetted by the main sequence. And then we see the galaxies are also fading. So these are galaxies which are quenching or essentially not forming stars anymore. And then we see them here, down here. And essentially what we can say is the star cluster population are found in the majority of galaxies in this type of plots. So this is maybe the first motivation why we want to understand star cluster populations. And yeah, we will go through the working definition of star cluster, which we will clarify in the next slides. And then we will look at fundamental tools to use star cluster populations. We will look at their sizes and masses. We will look at the cluster mass function, cluster disruption rates, and formation efficiencies. And if there is time, we will touch a bit on the early phases of cluster formation again, but this will be mostly JWST stuff. I've seen a very little JWST result presented, which maybe we can rectify a bit. So if you go on Slack, on the day 3 channel, you have this link. I'm not sure that this works, so you may try with your phone. You will go to a Padlet and maybe take 5 minutes and add there some, it's like online post-it site. You can write essentially what you think a star cluster, how do we define what a star cluster is, and maybe why they are relevant for your science, or if you happen to deal with star cluster in general in your science. So you can, each of you can add two sentences in the Padlet. I can show you how it looks like. Yeah, I see many of you are connecting already, but why doesn't show it? Yes, okay. So, yeah, there are 4 people now in, this is how it looks like. You click on this cross, and then it shows something where you can write. And here I have written, write both about the absolute definition. I mean, how do we know that we are looking at a star cluster and a working definition? Because there are obviously limitations. If you don't understand what I mean with these two things, just write what you would define a star cluster. And then another thing, write why it's relevant for your research, or maybe not, or why do you think looking at star cluster is interesting? We should also see appearing things while you write. Let's see who is the first that gets a cookie. Yes? Yes, wait a second, if I get my mouse on the right desktop. This is the code. Does it work if you use this QR code? Okay. While we wait for the images to come up, I actually had here also some figures. So we are looking on the top row at star cluster of different ages in the Milky Way. So this is what we call a young star cluster. It's a Westerlund 2. It's one of the massive ones in our own galaxy, a few million-year-old. Pleiades, it's what we typically refer as an open cluster, and a globular cluster. Stellar densities are clearly different between these three classes of objects. But in the way I talk about, for me, they are all star clusters, so they are not different classes of objects. And here you see again a sequence of different ages of star cluster. You see feedback, Melanie, sorry, Maya. I connected to your feedback later. And then you see star clusters which are aging, so they are more evolved. Are we 5 minutes past? Yes, so we can get out and look a bit at the answers you had here. Oh, nice. Okay, so overdensity of coeval stars compared to the galactic field. Yes. Yes and no. Yes, it is an overdensity of coeval stars, but those we can say it's also for associations, right? And associations do not survive very long. They are co-moving, yes, for example there. So I mean, yes, they are coeval, they are co-moving, but how do stars can be co-moving together for quite a long time, not simply a few million years? Let's go on. Gravitationally bound groups of stars. Indeed, that's the fundamental property, that they are gravitationally bound. And since they are gravitationally bound, they can move together, and we see them as coeval. They formed in a specific, under specific conditions, which make them gravitationally bound, and therefore also coeval. So the time scales under which they formed were very short, essentially. Okay, we have got the answer, and we will go back and read at the very end of the lecture about why relevant, the star clusters are relevant for your research. So now I've lost my slides somewhere. Why do I have this mirror stuff? Do you see my mouse? Yes, I see it. You can continue writing. Okay, so we are here. Indeed, so we are looking at gravitationally bound stellar system. How do we know the Westerlund 2 and the Pleiades, for example, they are quite young, right? How do we know globular cluster, they are very old, so we know by just looking at them, my goodness, they are so old, they must be gravitationally bound to hold together, right? But how do we know that these objects are gravitationally bound? How can observationally determine that they are gravitationally bound? No observers here in this room. Yes, Amy. Yes, exactly. You can do spectroscopy of their stars, and you can look at the radial velocity of each star, and then determine essentially that they are gravitationally bound. Yes? But let's assume that this is the absolute truth, because if we start to question the absolute truth, then we don't get, we cannot move away from our neighborhood, you know, in the solar neighborhood. Okay, but then now we are in the MT3, we are a 5 megaparsec away. Can we tell that these are gravitationally bound objects? Again, we exclude these ones. These are old. These are 1 giga-year old or hundreds of million year old, right? And morphologically, they appear compact. So somehow they must be gravitationally bound. We will go into why. But how do we know that these are gravitationally bound? They look compact, okay? But nothing else. We actually don't know if they are gravitationally bound, okay? So this is the working definition of studying star cluster population outside of the Milky Way in local galaxies. We actually don't know if they are gravitationally bound. So what we know is we are looking at compact stellar objects, and their luminosity are high. So here, this is a beautiful image from a Brad Whitmore paper on M83. You are looking at 1 kiloparsec size region in the spiral arm of M83. And you see there is a lot of clustering of blue stars. So you all know that we are looking at young star-forming regions. And then sometimes you see overdensity of these blue stars in very compact morphology. These are what we call star cluster in local galaxies. So how do we know that they are bound? Apart from the morphology, what do you need to say in terms of telling that it's gravitationally bound? If you think about n-body dynamics, how is a system gravitationally bound? I'll give you a hint. Come on, I know you can do it. Look, it's down here. Do you see it behind my laptop? Crossing time. What is the crossing time telling you? Have you all done Astronomy 101? Come on. Ben, okay, say it. Yes, or in the way I see the crossing time is how long it takes one star to cross the object, just the size of the object. So if the age of the cluster is larger than the crossing time, then we know that the star has been able to cross that region several times, to move in that region, the star cluster, several times. So we know it's gravitationally bound. And this is very fundamental when then we want to study star cluster population in general, everywhere I would say, but mainly for this lecture. So we go then to the way we work with star cluster population. Here you see this is old plot from one of my papers, but it's essentially what everyone does nowadays. We look at the morphologies, at the light distribution, and if you look at the top there, you see that the light of the star cluster is what we say the PSF is resolved. It's not a stellar point spread function, which is there at the bottom. Sorry, my arm is very short, actually. You see, this is a PSF in the image. This is how a star looks like in this image. And this is a star cluster here. And the light is distributed much broader, right? And in some cases, you see here that the light is not even, so there are 3 bright stars in this region. There is light, diffuse light around. But we are not looking at compact morphologies. So in our poor way of defining star cluster in local galaxies, we see compact morphology, then we call them cluster. We see multiple peaked morphologies, and we call them stellar association. Then what else we do? We have HST images, multi-band images. We do color diagrams. And now we are trying to extract physical properties from their lights. And here you see these are stellar evolutionary tracks of single-stellar populations. So here we are seeing a single-stellar population forming and evolving, becoming like giga-years old. And here you see that all the star clusters that we have detected in this galaxy line along this light. Now, on this side, we are looking at star cluster and associations in UV band. So we are very sensitive, UV color, we are very sensitive to the very young stellar population. On this side, instead, we are adding a color which is sensitive to older star cluster. And then we see that the density is higher at intermediate age. We are seeing a lot more of this object in this color scheme. Of course, when we look at association, there is something immediately comes up to the eye, and this is that there are not older associations surviving longer than a few tens of million years, and as it should be, because we already knew that if a 5 megaparsec or 10 megaparsec, they look like this, they are obviously not gravitationally bound. Their sizes are too large. So, but then with color, we cannot derive what we want to know. So what we do is we do ACD fitting. What is, we fit the spectral energy distribution of these clusters. And here you see, okay, here I'm showing a cluster now. We are looking at redshift 10 with JWST bands, okay? But here it's the same concept. We have these models. We have used them to produce color diagrams. And here we fit the light of the cluster in the different bands. Now, people who do galaxy studies, they have 6 bands and derive all these properties. And people who work on star cluster for 30 years assume some parameters here, assume that the star formation is instantaneous, and we know that if you have an optical UV color, you cannot derive metallicities. People doing galaxies don't care very much. Essentially, we all assume this parameter, and we go for 3 of them: age, mass, and extinction of star cluster. And now problems come up because we create this single stellar population here, assuming that the star cluster light is 1 million solar masses. And when you have 1 million solar masses, you can sample the IMF perfectly, from the most massive star down to the lowest free floating planet. So you can really fill it up. But actually, if you go to lower masses, you see that the single stellar population model that we used in the color plot is not working anymore. So actually, each point here, each color, sorry, is a bit out of focus, this plot, is showing you that the cluster light will look more, we spread around the track that we used as reference. So this is what we call ACD fitting with deterministic model versus stochastically populated models. So now we are creating model libraries with the million realizations of cluster light where we sample stochastically the IMF. And you see, it's not only important for the very young ages. So actually, here you don't see very much the effect because of the stellar population that in this work they were using. But if you use a BPAS, also here would be huge, the spread. And then you see starts the spread here, which corresponds to the red supergiants, and so on. And then you see AGBs growing here. So, and here we are at 10 to the 4, and then we are at 10 to the 3 solar masses. And this is, we are plotting here ages versus color. So this is how the color of each of these single cluster realization looks like. Now, what we should do when we fit star cluster is to use this type of libraries, and of course Bayesian inference of, because we cannot find a single solution. We have really to find the most likely one. we have done that, and we have compared what we see when we use a deterministic model or stochastically sampled model to fit the age, mass, and extinction. So all the other parameters have been assumed. And here you see that the largest spread is in the age that we derive for the star cluster and the extinction, because they drive the color. The mass you can think of as kind of a normalization, although it's not really true for stochastically sampled stellar cluster. But in general, you see that the spread in the color happens below 10 to the 4 solar masses already. Is significant. And that's also that the extinction then becomes really different in the two way of analyzing.
What is the metallicity assumption here?
Here we are looking at solar metallicity. We fix the metallicity morphologically is a spiral. Usually, yeah, we fix the metallicity to the nebular abundance measurement we have.
Possible to collect it from the color of the cluster?
Well, you have optical color. If you cannot distinguish metallicity in optical colors. Yeah. Okay, so let's try to move on. So now we have the light distribution. We saw that the light is more extended, the single stars. So we can actually derive the effective radius. This is the half-light radius of star cluster. And in this work, they looked at several galaxies. In total, they had more than 16 galaxies, where they look essentially at how is the size distribution of star cluster. And this line shows the detection limit, so what the PSF of each of these galaxies would look like. And you see that the peak, so the shape of size distribution of young star cluster in the local universe is log normal with a peak between 2 and 3 parsec. If we plot, so this is the sample that they've studied, and then add some literature data from the Milky Way and also other massive cluster on these regions here. What we see is a very shallow size-mass relation. So if you remember from Mark, he said that the giant molecular clouds that these star clusters are forming have a size-mass relation, so I have a constant surface density that is telling you that the mass scales as r squared, or that the size scales as 1/2. So you see that here for the star cluster, this relation is much flatter. So that translates into the fact that it's very weird that in the local universe, we see star clusters which have a peaked atypical mass of 2 to 3 parsec with some spread, which is not expected if you do the one-to-one relation with giant molecular clouds, which tells something more about their formation. I continue with some other result of the same paper. So I'm looking here at the Brown and Ned in 2021, because they also looked at so the properties, the mass, they use the mass of the cluster and the surface density. And what they see is that when you look at cluster between 1 and 10 million years, the surface density of this cluster is quite low, and you are looking at on average, a very low mass cluster. While when you look at age ranges older than 10 million years, you are going up in terms of mass, and of course also in terms of density. Remember that the radius change in this entire sample is very shallow. So what is changing here essentially is mainly the mass. And we see that for ages above 10 million years, cluster have, in the local universe, stellar density of 10 to the of 100 solar masses per parsec square. And then they also look at this bound, so how many of the star clusters, if we have a size and mass and ages, we can also derive how many of these star clusters have an age or longer than their crossing time. And you see that essentially for the very young sample, the very young cluster, very small fraction, actually, it depends also on the mass, of course, it's bound. So we are looking at objects that all this tail here will disappear in 10 million years' time. While if we look at older ages, then the fraction of bound cluster in the catalogs is very high. So we have established that after 10 million years, we are more confident that our observed catalog have a bound star cluster. What can we do with them? So we can look at the cluster mass function. And so we have looked in the literature. Now it has been 2023. I think the first time we discussed what is really the shape of cluster mass function was 2006, the first publication. So I would say 15 years we are debating what is the real shape of the cluster mass function. And here I put the power law shape, which I hope everyone assumes it is. And on this side, you are looking at a truncation added to the power law shape. So it's an exponential cutoff at a characteristic mass MC, which essentially would describe what is the typical maximum mass that a local galaxy can form in star cluster. So what is the maximum mass a star cluster can have in a galaxy. So I would like for you to go now. There is also a Jupyter notebook. I don't know if you already downloaded. For you just to understand what it exactly means if I assume a power law without a truncation, so without an upper mass limit, or if I assume this type of power law with an exponential cutoff, when I sample the cluster mass function, what does it mean in terms of population? So there are two exercises that you can download, you can work on. The first is very easy. It's just for you to see how it changes the maximum mass of a cluster population if you use these two power law distributions. You can work together if you don't have your laptop here, or it's totally fine to work together. Yes, I actually have cookies from Sweden. So after the lecture, please come here, everyone, and get a ginger cookie from Sweden. I know you tried them at the IKEA, but these are better. They are pepparkakor, they are called in Swedish. If you feel like you are too tired to run a Jupyter notebook, tell me, I will give you a cookie now. Raise your hand if you need energy now. Yeah, I'm coming. It smells like Christmas. Thanks a lot. Cookies? Sugar? 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 No? Sure? Sugar? Sugar? But you have to try now. It's okay. Tutor can have cookies too. Yeah, well. Are you sure? You have worked the hardest. Come on. Ooh. John, you get a cookie, it's fine. Pedro. Sorry, Maya, I called you. My brain doesn't work properly. Did it work? Yes? I leave them there so you can take more. Cookies? Are you sure? Bjarki, you can take two. I know you are homesick. I was going. Did you manage? Maybe it's too easy. You are done already.
Indeed, they are much better than the IKEA one.
Yeah, they are better than the IKEA one. Cookie? Are you sure? Okay. Did you manage already to run? Are you sure, Ignacio? You don't need sugar? Go ahead. Can you pass the... Sure. Cookies. Cookies. Sure? Okay. You got too much chocolate yesterday. Okay, so let's move on because actually we don't have much time, but the change in the numbers in exercise 1, did you all manage to do exercise 1? Yes? Yeah, I see heads saying yes. Essentially, the change in the number of clusters is what we call a size of sample. So if you have a higher star formation rate in the galaxy, then your cluster population will have a higher number of clusters, so it would be more populous. And yeah, this is essentially here said in this sentence. So what was the first question exactly that I asked in exercise 1? Can someone read it? Yes.
What do we need to statistically determine the truncation mass? That's at least the last question. How many clusters more massive than the truncation mass are found in the two distributions? If the truncation mass is 10 to the 4, and how many if the truncation mass is 10 times to the 6 or 6 times 10 to 6? Answer the question both using populations of 100 and 1,000, 10,000 clusters. What do we need to statistically determine the truncation mass?
Okay. So did you find the cluster more massive than the truncation mass for 100, for n equal 100? How many? For the Schechter function, not the power law. Okay. With the 100, n equal 100. Yes. Okay. So, but the result is if you have 100 cluster and you sample the mass function with that truncation, you will not find a more massive cluster than that truncation because it doesn't have enough number to populate well the upper mass end of the mass function. Unless you have a power law. Then if you have a simple power law without truncation, you find them. Maybe that's your answer. You find them always. So the way to distinguish whether a truncation is present or not is to have a populous cluster population, so to have enough star cluster in your population. So this is the solution for exercise 2. I didn't produce this plot. This was actually done, was already available in the literature. And here you see the dotted line is showing you what happens if you sample a power law without an upper mass n, so a power law without truncations. And the solid lines here show you if you have a truncation of 10 to the 4, 10 to the 5, 10 to the 6. Ignore the dashed line because we don't do the luminosity. And essentially, if you have a cluster population with 1,000 clusters, you can determine if that population has a truncation mass of 10 to the 4, but at 10 to the 5, your signal is too weak statistically to be significant. So you do not find a real significant truncation there. If you want to determine at 10 to the 5 solar masses truncation, you need already a few thousand clusters in that population, and so on, okay? So now you can understand this type of paper and statistics. I'm reporting here results from Weiner 2022. They are looking at star cluster in M33, so it's a very local galaxy. Actually, the stars in the cluster can be resolved, and the ages and masses have been derived not from SED fitting, but using color magnitude diagrams, so the light of the stars and the fitting isochrone to their distribution. These are the best cluster properties, physical properties, and the most robust outside the Milky Way, okay? And they have thousands of them, and then they look at the ones which are more massive than 10 to the 3 solar masses, and try to determine the slope of the mass function, the cluster mass function, and the truncation. And you see that they have in their marginalized distribution, in the corner plot, their fit essentially converge, and converge to a specific truncation mass of 10 to the 4 solar masses and a slope of -2. This is the fit for the slope. If you don't use a power law truncation, it becomes much steeper. And indeed, you can see the observed luminous power law mass function. So this is the observed mass function. This is the realization using the 68% from the fits. And this is the power law distributions from the same fit. And you see that that power law distribution is totally missing the real distribution of the cluster. Then you can count how many clusters more massive the truncation you have. Observationally, it's this black line, and in blue is what is predicted with the a truncated mass function, and in red is the power law mass function. And you see that statistically, the pure power law is not compatible with the observed mass distribution. Now you can do that in many galaxies, and here I plot what we do sorry, this is still a plot from Weiner. You see there are, on the x-axis, the plot star formation rate density. So essentially it's how many stars are formed, not just, it's not star formation rate, but in units of area in the galaxy. And you see that the truncation mass that are derived in these galaxies is scaling with these properties. And the star formation rate density, as Mark showed in the previous lecture, is connected to the gas surface density in the galaxy, right? Via the Kennigat-Schmidt law or the Bigil subgalactic scale law. But there is a correlation. So this correlation is telling you the galaxies that form their stars with a higher rate and in more compact areas can form more massive cluster. And this is very important then when you want to include star cluster formation in, for instance, in simulations, or if you want to understand the cluster population that you see. And actually, a similar trend is also observed with the much larger scatter for a giant molecular clouds population. So we see that the truncation mass of the mass spectrum of the clouds is changing as function of star formation rate density in the galaxy. Again, I'm not saying that all these clouds here are forming this cluster here, you know, it's not a one-to-one correlation, but statistically there is a trend. So this is a bit the plot that I had originally. It looks the scatter much larger than in the Wiener, but I will not go into the details, there is not time. But now you understand. So instead of looking at a single galaxy in this plot, I combine them into this super galaxy, because if locally they are similar, they have similar star formation rate, then we expect the mass should be similar. And that's what I've done here. I created this super galaxy where we can increase statistics, and now for the spirals we have more than 4,000 clusters, and we can derive with confidence their truncation mass. And here you see the 4 dwarfs. We don't see that. So don't dwarf have a cluster population in dwarf, don't have a truncation mass? That was the, well, we have not found it, and we try to understand why. Is an environmental effect, what is causing that? You see, this, the dashed dotted line shows you the range of star formation rate density probed by the dwarf sample, which actually has a very low number of clusters, 375 in total. So you see that the lack of convergence for the truncation mass is simply due to number statistics. And if we could double, that was a study done with the Lagos survey, if we double the sample of dwarfs, what we see essentially, we will find statistically a clear signal if the truncation mass is there. So now we move on into cluster destruction. So you form them gravitationally bound, and then you have to find a way to destruct them, okay? And actually, nature helps, because they have to come out of their gas. Although one can say at the scale, if you look really at the scale where the stars are gravitationally bounded, there is no gas. So maybe this destabilization from gas expulsion is not too important, or is there, but actually it makes them already unbound from birth, as you can see there then in the next column. And then you have stellar evolution. You lose mass because the stars start to explode into supernovae. And you have N-body interaction, which make the low mass stars to be, and also mass to be ejected from the cluster. So essentially you have what is called evaporization of stars. And then there are external processes. So the cluster is forming in a giant molecular cloud, and that gas which is left, destroyed, all that part is affecting the star, the potential of the stellar population just formed. So maybe already at birth there is a dramatic reduction of number of clusters that then will be gravitationally bound. And then there is the galactic tidal field, which is in the galaxy, but there are also tidal shocks, and these are more periodic and will be encounters with giant molecular clouds, and spiral arm passages will affect also the stability of star cluster. And then, of course, dynamical friction. Observationally, it's not so complicated. We will not look at each single process, but what we look is at the number of star cluster, again, as a function of time. So we are very poor, the observers are very poor in their approach. Essentially, if there is no disruption, then the number of clusters should not change with time. If there is total disruption, it doesn't matter, then you should see a rapid, the number should go down significantly. And there is another way. So actually, if you account for the fact of the external interaction that cause disruption, you should expect to see a dependence of the mass in the disruption. So low mass cluster should disrupt first, and then slowly the high mass one should disappear. And then if we look at their number rate as function of time, it should look a curve that is constant and then it turns down. This is where we start, and now I have to be honest with you because there are many uncertainties. First of all, when we observe a cluster population, we see that we never see that it's fully populated all the way to all the mass range. So actually this is the effect of detection. If we do our completeness right, then you see that we do not detect cluster below a certain luminosity, but that luminosity gives a different mass cut as function of age. Then, why are clusters in the 1 to 10 million year less massive than in the 10 to 100 million year? I had an exercise, but we will be here for too long. So if you want, you can play with that. But essentially, why we have here less cluster than if we look at the number in this age range, 7 to 8. Do you have an answer for that? What is different if you are forming constantly star and the star cluster population is replenished constantly? What is changing between this range here and this range here? Time, right? Time is longer. And we said that the size of sample, right? As you have more cluster, you have the likelihood of sampling more massive cluster, right? So what you expect is to have more cluster in this range than in this range, right? Because you have passed more time. But since the detection limit makes this very difficult, we can look at the very massive one. So you see that the top one here, the very young ones, are all low mass. Is this galaxy a weirdo? No, it's not. It's simply that here the time to sample the mass function has been very short, while here we are combining several populations, and therefore the likelihood of sampling more massive cluster is higher. So what we can say is if disruption is mass dependent, we should expect to see this trend going up because we are not disrupting the massive ones. If it's mass independent, we should see them disappear. It doesn't matter what mass they have. And then there are several assumptions, constant star formation history. Otherwise, you will see enhancement, and the number of clusters are going up and down depending on the star formation rate. So for spirals, this is what we assume, it's constant. We have assumed a mass limit, and this is why you see this shadow area. So we cut and we look at the DNDT over a range of mass that is complete. So we remove all the incompleteness. We look at the same mass limits. And then, of course, there are age uncertainties due to degeneracy between age and extinction and stochastic sampling and so on. So it's a nightmare, actually, to look for a signal. But here you see essentially the associations that we had at the beginning disappear very rapidly. It doesn't matter what, but I think what we see now with the studies of Milky Way association with Gaia is that these large associations are not bound from the beginning. So they are simply expanding, and that's why we see them disappearing. While the cluster seems to survive and stay there for a while. So now I've been a bit dishonest with you because not in the literature actually there is a wild difference, even looking at the same galaxy, whether there is cluster disruption or not. So, and here it's a review from Mark. You see from catalog, which he called exclusive and inclusive. In this catalog, they do not has a lot of association that will disappear, if you remember a few slides ago. While here it's like the catalogs have been clear of all noise, but again, it's not a one-to-one correlation. So there is still not a conclusive, there is not a conclusive agreement on cluster disruption, youngster cluster in local galaxies, and probably the observational bias are creating the discrepancy. But there are also some nice and interesting signals. For instance, if we look at M51, what we see is the disruption in the center of the galaxy here, where the gas surface density of the disk is much higher. The disruption becomes much significant. So we are at 90%. If you look at the star there, the yellow points, 50 to 90% of their cluster are disrupted independent of their mass. While if we go in the outskirts, we see less disruption. So if you are a cluster and form in the outskirts, you have a higher likelihood of surviving for longer time, but not very long. And finally, in the last 5 minutes, we can talk about cluster efficiency, which is again debated and not concluded. But here you see that we can count what is the total mass formed in star cluster with respect to the total mass formed in stars in the galaxy. So gamma is a fraction between 0 and 100%, depending if all your star formation is happening in cluster. And actually, there is also a model proposed. So I have all the references. Yeah, where this fraction depends on star formation efficiency, gas surface density, on the stability of the disk and the potential of the disk, which is dominated by the stellar surface densities. So what is the fraction of stars forming in bound cluster? To derive this gamma, we divide the total mass formed in star cluster divided by the total stars formed in the galaxy over the same time scales. And now I was not here, but I guess in the first day, they introduced you to the uncertainties of deriving star formation rate with tracers. And now we are adding the uncertainties from the star cluster. So I hope you don't have your hopes very high for a correlation. But there is some sort of correlation with a lot of scatter. This is an old plot. I'm plotting here the Krausen model, which depended on those galactic quantities. And then you see in 2016, so the model depended on gas surface density and was converted using the Kennigat-Schmidt relation. And this is the solid line. And actually, if we use the Big Hill conversion, which Mark discussed a few half-hour ago, so the atomic and molecular transition of the Kennigat-Schmidt relation, the Krausen prediction changed a bit and kind of reproduced the scatter within this data. But now there is also a consideration what type of tracer we are using in that plot. So all the symbols you see in blue, we used H alpha. So we were using a very short time scale of 1 to 10 million years, while all the green plot points here used a different tracer, which traced the 10 to 100 million year range. And therefore, you see the relation, what could appear as a relation, seems to be driven simply by the selection of the time scales. And so this is a result from Chandar et al. They suggested that actually there is no relation, that the cluster formation efficiency is constant over this large range of star formation rate densities, and is simply caused by disruption. So here you are disrupting clusters, so you go lower, and here you are even disrupting even more. Although these green points are not reproduced by their model, the 3 to 4% survival rate. Okay, so then what we did is, that's true, is a consideration to take into account. So here we divided all the data in the literature depending on the star formation rate tracer. So here you see the baseline 1 to 10, and here you see the baseline 1 to 100. And the scatter is still there, of course, it has not diminished, but the trend is also present, maybe yes, maybe not. There is no way to clean the relation here, because all those galaxies are too far to use other tracers that are like counting stars and so on. So at the end of the day, we suggested just to put all together, and we proposed this median trends for the observations, and we discussed what is causing the scatter. And so we also compared with simulation. So here you see in this simulation clusters were forming over a gas surface density criterion, and then the star formation efficiency was changed in the models, and you see that the cluster formation efficiency they derive kind of overlaps with the observation. In the e-mosaic simulation, clusters are added to the zoom-in simulation of galaxies with the prescription, the Krausen model. So in a sense, they kind of reproduced extremely well the observation, but it's also a bit unfair. And recently, Mike also had a simulation where he tried to simulate the Milky Way assembly. And you see cluster formation efficiency in the simulation changes a lot depending on what he uses to derive the number of clusters and the total mass. And the purple line here is when he uses a grid. He uses only the boxes where clusters are and stars are forming. So it's like focus a bit more where cluster formation is happening in the galaxies. So, okay, I will not discuss the dwarfs, which are always a nightmare. But essentially, if we use the 1 to 10 millimeter, there is no correlation with any of the observations so far. So they lie very high. It looks like 100% of the star formation is happening in cluster. While if we compare the star formation rate tracer, now for the dwarfs, we can count their stars because we can look at the stellar population. We see that actually if we use the star formation history base, so if we count the stars and we use more robust estimates of star formation rates, we can see that the gamma changes. So this gives you an idea. You see the point came down to observation with a lot of scatter still. And then here we were including 1 to 10 million year. So what we did is, if you remember this plot, the 1 to 10 million year in the sample are really not, a large fraction are not gravitationally bound. So since we have a star formation history, we can focus also on the 10 to 100, which is this one. This one. And here you see. So now we are looking at the cluster population in this age range and the star formation is, so we are counting the stars actually that we see in the same range. So yeah, it's not concluded though. There is no consensus, so I cannot give you a conclusion. And unfortunately, I have to skip the JWST stuff, but yeah, sorry. Yeah. We can go to the conclusion now. And go back, so the last slide here was about what do we care about star cluster formation and statistical properties. So I go back and bring up yeah, your pod. So let's see why you care about the star cluster. Did anyone answer the question about why star cluster is relevant for your research? I work with massive stars and feedback, observational, and that's unavoidable work with stellar cluster a lot. Yeah, exactly. So we care about the mass function because we want to know how many massive clusters. So the massive cluster are the key units for stellar feedback in the galaxy. There was yesterday someone showed what happens if you have a distributed supernovae or clustered supernovae. And the ISM shape morphology is clearly telling you that you need a clustered supernovae. So yeah, that's why we need to look at star cluster population. Any other answer? Research is on forming high mass star cluster. Cool. So did you find them? Did you manage to form a very massive star cluster? It's quite complicated actually to simulate giant molecular clouds forming very massive star cluster. It's impossible to get rid of the gas in simulations, but in observation is not. So this is observations. So these are in the center of the Milky Way. We are looking at a very massive cluster.
It's an interesting question. Do we get rid of the gas or do we accrete the gas?
You mean the star cluster accrete the gas? No.
No, I mean, you refer to this possible problem that in observations and simulation you say the very massive cluster we do not get rid of the gas.
Yeah, yeah.
But are you sure that in observation we get rid of the gas or do we just accrete the gas? Because we will get rid of the gas in simulation, we just accrete it. I mean, we return like 100% efficiency of stars. So is it incompatible with observation?
Well, I mean, all the massive cluster we can see after a few million years. 10 to the 6 solar masses cluster have bubbles opened. And I don't think the simulation managed to open bubbles so fast.
But the bubble, is it because you have diffuse gas around that you would not have included in the simulation?
It's the H2 region of the expand H2.
We'll have H2 region.
Yeah,
in
yeah.
the massive cluster. What happened that this H2 region is not strong enough
Mm-hmm.
to unbend the gas. But if you have gas around, that was.
Yeah, yeah. Okay, yes, I am. Yeah, it's also, yeah, but so. Good question. I don't have an immediate answer.
It's a very important question because
yeah.
What is behind is whether we are doing the feedback well. And,
yeah. Yes, Nuria.
I just wanted to quickly say, I don't think that the distinction between associations and clusters is so straightforward with Gaia. What I was showing on Monday is that in fact we are seeing many things that seem to be in between. So I think the picture is a bit more complicated than this.
Yes, but the in-between, so these regions which are in the in-between have a crossing times, which are like of the order of few million years, and they are also young, a few million years. So it's also difficult to determine what the stars, so it's too.
So exactly, but what we are seeing is clusters that have coronas that have tails, so clusters that maybe the center is round, but the outskirts are dispersing.
Yeah, yeah.
I think the distinction between what is a cluster gravitationally bound and association.
You are fine. So you are totally right. Star clusters are never forming isolated. Star clusters are forming inside associations. But the star cluster will have a size of 1 to parsec, like Cygnus X, or one of the big where Trampo 14 is, what is called that big regions. Trampo 14, Trampo 16, Eta Carina, the Carina Nebula, yes. That region is huge, it's 50 parsec, and it has two band clusters, the two Trumplet cluster, while the rest is an association which is expanding. So we do not expect to see an idealistic star cluster with an H2 region. We expect a star cluster, clustered star formation in terms of OB associations. So it's true what you are saying. The bound cluster will stay, the clustered regions will expand. Yeah.